100 5G labs across 100 academic institutes. Inspired from that, we also came up with a similar solution which can be used as a test bed in the academic institutes. The advantage includes, see, and universities actually now scenario changed. Previously, they used to work on only on research, research and theory and all. Now, they are moving to labs and then working in the practical scenarios. Then this will give the practical insights of end-to-end 5G system. What is the 5G system contains? What are the main modules of that? How protocol, how user equipment, a device will connect to the 5G network, and what are the protocol information exchange between UE and other 5G network entities. So it will give the practical insights. Yeah, then and then a deeper, it will give the, actually NEO will go through the specs and it will give the deeper understanding of 3GPP specifications of 5G RAN core. See, NEO will go through the 3GPP spec and will implement the modules. So this two will go parallel, parallel. So we'll go through the spec and we'll implement and we'll see in the practically how it is behaving. And then hello, ma'am, am I audible?
Yes, sir, you are audible, sir.
In between, okay. See, then see, after having this solution, so you can enhance the system capabilities. This is see, suppose some release support. So you can add next release support to this system, and then you can test the system. You can add many more use cases. You can add some IoT use cases that I am going to cover in coming slides. Then not only use cases, this will give the foundational basis for the 6G research, and from that you can generate IPR. See, why I'm telling is this, I'll rightly correct this, how it is useful to the 6G technology, because 6G is mainly building on 5G technologies only. This is basis for 6G, and they are enhancing 5G and adding new use cases, which actually in previous session sir was covered. So these are some of the advantages of the 5G university solution. So how university solution looks, architecture looks like. See, so the main elements of the 5G network includes 5G core network and IMS. Core network is for data related functionalities, and IMS for voice and video calls. Then when it comes to G Node B, as I mentioned, G Node B contains two modules, CU and DU, CUD and DU, and then this is the second element. The third element is the radio unit. Radio unit is for transmission and reception of the signals over the air to the user equipment or devices. These are three elements very important for any 5G network. This is similar to 5G network. So it's a scale down network, scale down solution which can be used for research purpose. This is about the architecture. So what are the system specifications? These are some of the system specifications. It is 3GPP release 15 compliant, and then in India there are two bands auction, N78 and N28 in FR1. So it supports both the bands. And then when it comes to MIMO configuration, you can configure up to 2 TR and then test the system capability. Then subcarrier space. These are the physical layer specifications. Subcarrier spacing in TDD it supports 15 kHz, and FDD it will supports 30 kHz subcarrier spacing. Modulation support up to 256. You can configure from QPSK to 16 QAM, 64, and 256 QAM in uplink and downlink. Bandwidth NEO in 5G they define when single carrier bandwidth is 100 megahertz, but this is a scaled down version, so it supports up to 50 megahertz bandwidth. And transmit power per antenna port is 100 milliwatt, which will cover around 25-meter range in TDD. And in FDD the range will be more. Then it will use around 50 to 60 meters in when you run that in a FDD case. So through throughput we have observed in our lab up to 160 Mbps approximately. And then you can make VoNR, VNR with voice and video calls without any internet. Is IMS calls. Then capability, when it's device capability, see 128 UEs you can connect, and parallelly I can access the 5G services. These are some of the system specifications. So, and what are some of the IoT use cases we have integrated with this university solution? There are some 5G enabled IoT use cases available in the market. We have procured a 5G enabled camera and drone and cellular router and 5G CPE. These will directly connect to the 5G, and you can check the functionality. 5G camera is for mainly for surveillance purpose, drone for aerial surveillance purpose, and then cellular router is for one side it will connect to 5G, and other side via LAN cable you connect it to PCs or wherever reliable connection is required. And 5G CPE, 5G CPE again it's similar to cellular router, but one way it will connect to 5G, other side it will provide Wi-Fi. So through Wi-Fi, so another 256 devices you can connect, and you can increase the capacity and access the 5G services. Then along with that, we have developed some of the IoT use cases where 5G is not enabled using LoRa technology and a gateway, which includes light sensor and motion sensor. Motion sensor, it is agriculture use case where and if you place the sensor, if someone is entering into your field, and then it will give the motion detection and it will give the alerts to the farmer. This kind of applications, and the water level sensor in a tank, and then temperature and humidity sensor and moisture sensor. Actually, you can place this in the field soil, and then you check the moisture. And moisture, if the moisture is going down, it will power on the motor automatically. So this is one such use case. Then ultrasonic sensor, it will detect the objects water levels. Then TDS meter. TDS meter is for checking the water quality of the water quality. So these are some of the IoT sensors we have built and we have integrated with this solution. And along with that, gas, vibration, and pressure sensors also we have included. So with this, we included and we have created one dashboard where you can monitor continuously these parameters. So along with this, you can come up with your own use cases using this solution. And then what is, see, when the device is, when your network is on, when you are trying to connect a UE to the networks, they mainly will heard about actually call flow, where how mobile will connect to the network. See, that call flow you can practically see using the Wireshark. When mobile is connected, you open the Wireshark, then all the messages, how message is flowing, what are the message content, and how, what is the each and every information element you can understand. It includes, suppose call flow includes when mobile is connected to the network, it includes registration requests and authentication, security. It will provide you UE capabilities and repudiation establishment, what is devices, how devices getting the IP address. All those things you can analyze using the Wireshark when your system is running, when your mobile is connecting. Not it is just NGAP. Not only that, and they have 3GPP defined F1 AP, that is for between CUDO. You can capture the F1 AP protocols also. What message flow is happening between CU and D. So this is one of the advantages. Practically, you can understand. You can compare with the signal our specs and what is happening. It's a deeper understanding of the 3GPP specs. Another such use case is network parameter monitoring. As there's a app called NetMonster. You can install NetMonster in the device. You can connect the device to the network, and then you can check what is the power, RSRP, received reference signal received power, and then what is the cell ID, what is the tracking area code, and then what is the physical cell ID. All those things you can monitor using this. This is network monitoring. Another is IPOF testing. You can test the system capability, system capacity using this app. These are Aruba utilities. You can, it is online available free app. You can install, and then you can test the capability. Then what is going wrong, what is the error rate, all those things you can measure. This is one such use case. These are some experiments you can do using this solution. And along with that, not only that, see, you can change that when it comes to TDD configuration, slot configuration can change and check the system performance. You can change the modulation scheme, MCS modulation coding scheme, and check the system performance. All those things you can play around with this solution. It is see, flexible, and you can understand very easily. Then you can add use cases. Not only that, you can debug the GNodeB source code as using Visual Studio Code. How to debug? You can put in some functionality, some channel you want to decode, some PDSH, PUSH you can decode. You can place a breakpoint over there and run the code, and step by step, like MATLAB will go step by step. Same way you can go and check the each and every parameter, each and every variable, what is the function, how it is varying, and you can understand thoroughly using this debugging tool. Oh, this is one such. This is another such advantage of this solution. And then see, when you procure this solution, actually we will provide an actual solution in a box, and along with the antenna, some test SIM cards, and end-to-end user manual, which can be you can go through the user manual and conduct these experiments, and some will give some training, and you will support. And then any wireless communication, any cellular communication, you required one experimental license to the transmit over the air. So this will provide you WPC license also. And then along with that, this is actually if you want mobiles and CP idle users also, you can will provide you at an additional cost. This solution is established at 3 universities, Gauhati University and MITS Gwalior and the RVR JC College of Engineering in Andhra Pradesh. They are making use of the solution. Constantly they are in touch with us. Whenever they have some issues, they are supporting them. And then they have created lab out of MITS, especially they have created lab out of this, and they are conducting labs based on the solution, and they are coming up with the another new use cases using this solution. Ma'am, do you have time? So another 5 minutes I need.
Yes, sir, we have time. You may continue, sir.
Okay. So this, so the how 5G university solution is relevant to 6G. So that's that in previous sessions are covered in detail about framework of IMT 2030 for 6G and all. Then I'll just briefly touch on how it is university solution is relevant for 6G research. So framework for IMT 2030. So there are 6 usage scenarios. Among those, 3 are enhancing from the 5G previous technology only in this massive communication from EMBB and massive machine type communication from massive communication, and the URL to hyper reliable low latency communication. Other than these 3 use cases, they came up with the ubiquitous connectivity, where connecting to terrestrial network to non-terrestrial networks to serve the underserved areas, where rural areas, hilly areas, wherever network connectivity is not there. Then integrated AI is integration with the communication for network automation for increase the efficiency, and then sensing using this same technology. You can sense the objects and environmental objects, all those things. Use the same thing. So these are some of the these are 3 new use cases added to the framework of 6G, and then this is also based on they are enhancing the 5G and adding the 3 use cases. Then when it comes to capabilities, same latency, they have improved latency, reliability, and security, more secure and resilience and mobility, peak data rate, then spectrum efficiency. The 9 enhanced capabilities from 5G only. They are enhancing from 5G only. Then 6 new capabilities which are relevant for sensing, AI, and ubiquitous connectivity. As a coverage for ubiquitous connectivity, which is covering across the world. Means undercovered areas, including terrestrial and non-terrestrial networks, integration and sensing, AI related sustainability is in more energy efficient systems. They are coming up with the interoperability. So these are 6 new capabilities. So though they are building on the 5G, so if you understand the 5G solution, the solution will be useful for a 5G understanding, and then so same solution can be used for 6G research. Okay, then it is more relevant for 6G research and adding the new use cases. When it comes to spectrum also, they actually their plans to reuse the existing 5G spectrum and coming up with the hello. Any queries?
No.
Now I am audible.
Yes.
Yeah. So when it comes to spectrum, see, they wants to reuse the same spectrum which is defined for 5G, and they are coming up with the new spectrum. So main low frequencies for extended coverage, low bands, and then where actually see, but their interest is to define the higher bandwidth, larger bandwidth for uplink and downlink. So I mean, this is 400 megahertz for uplink and downlink. So they are looking for bands where this band is available. So main focus is recently I have TEC organized one international workshop on 6G. So I have attended that. From that, I understood that they are focusing on this one new frequency band, that is 7.125 to 8.4 gigahertz. So which will give the wide area capacity and data rate boost. So other than that, they are using the existing spectrum. This is of the spectrum. This is also spectrum also is coming from 5G only, and then another extra frequency bands they are adding to existing spectrum. So KPIs, 6G KPIs, so based on 38.914 is 6G scenarios. There is a technical report available. So peak data rate, see they have targeted for 1 Tbps, but as of now they are trying to achieve in 6G 36 Gbps for downlink and 18 Gbps for uplink, and spectral efficiency 16 bits per 60 bits per second provided for downlink and 30 for uplink. And control plane latency they have slightly increased 20 milliseconds, and then user plane latency they have as is they have maintained the 5G user plane latency. Reliability also is the same as 5G, and connection density also 1 million devices per square kilometer in urban environment. In mobility also 500 kilometers per hour. Why I'm actually stressing all these things means these are all similar to 5G. So if you go to this solution, so this you can easily adopt 6G technologies. You can come up with the new IPR in 6G. You can file the patents. You can and ACPs, all those things. And one other interesting fact is that, so when it comes to radio physical layer also they want to continue with the same 5G radio physical layer. So when it comes to waveform modulation, the discussions are going on. They are almost agreed that. And then when it comes to uplink, there is OFDM and DFT. So DFT spread OFDM. The same they are continuing. And then downlink cyclic prefix OFDM. And then sub-carrier spacing also they are initial purpose they are retaining the same thing, and then QAM is a base for 6G modulation, 6G radio modulation. Frame and slot duration also as is with the 6G. So this solution is more it's more relevant for 5G and 6G also, 6G research also. And not only waveform and modulation, when it comes to channel coding, they are continuing the LDPC for data, and then polar codings for control channels. These are some of the radio physical layer they are retaining same as 5G. Okay, then this solution will be useful for working on 6G also. So this is a way that solution, how a solution is connecting from 5G to 6G. Thus I'm trying to connect from 5G to 6G. What is the way it is relevant from 5G to 6G?
एक मिनट यहाँ आना बेटा.
Hello. So in conclude, this 5G 6G has started. 6G research has already started. They have came up with the Bharat 6G Alliance. They have launched the Bharat 6G Alliance in 2023, and then till 4G we were technology adopters. Now in India is no more technology adopter. Is a technology contributor, standards contributor. And then we have started 6G research early. So India will become actually as actually they have came up with the 6G DPR DPR for up to 25 to 30, which in previous sessions sir was explained, and then there are some targets. If we achieve targets, we execute that plan, thus India will become the 6G leader in the leader in the 6G technologies. Okay, so then in the ways of that 5G university solution also more relevant for 6G. If you understand 5G university solution, if you go through, if you add use cases, that is more of it will act as a basis for 6G technologies. With this, I will conclude my presentation. If you have any queries, please. Hello.
Any queries? Any queries? Yes, audience. Any queries? Anybody want to ask anything?
Please continue, sir.
Thank you so much, sir, for such an insightful session, especially covering the starting of the 5G use cases, then C.5G university solutions, and also you have discussed about the LoRa sensors, and so that we can use them on the as a use cases for this 5G. Besides this, you've also talked about the online app that we can use, that is IPER-F app, for measuring various parameters, sir. Thank you for such an insightful session, sir. Now I just kindly request you to kindly take the certificate of appreciation and bank of honor, sir.
Thank you.
Thank you,
Thanks.
sir.
Thanks.
Yeah, thank you, sir.
Thank you, ma'am.
ma'am.
Thank you so much for the opportunity. Thank you, Chaya, ma'am.
So now we move to our third technical session, where we have the privilege to hearing from another eminent academician and researcher in the field of terahertz technologies. So I would like to invite Dr. Bharat Sharma to kindly come forward and introduce our esteemed guest to the audience. Sir, over to you.
Very good morning to everyone. I'm audible?
No, sir, little louder, please.
A very good morning to all. It's a very great pleasure and privilege to introduce our distinguished speaker for today's expert lecture, Dr. Ekant Sharma. He's an assistant professor at the Department of Electronics and Communication Engineering, IIT Roorkee. Dr. Sharma is a dedicated academician and researcher whose work focuses on advancing modern communication and signal processing techniques. He has done his BTech in EC from Chhatrapati Shivaji Institute of Technology. He has done his MTech from IIT Kanpur, PhD from IIT Kanpur, and he has a expertise of 70 plus research journals, paper, conferences, and 8 plus patents. Also, he has some completed 10 plus projects and also continuing the research area in the field of 5G technologies. As a faculty member of an India's premier institution, he has actively engaged in high quality teaching, cutting edge research, and mentoring the students in area of signal processing aspects. Today, Dr. Sharma will share his knowledge and expertise on the topic software-defined architectures for 5G and beyond, from test bits to the intelligent infrastructure. So this lecture will provide the valuable insight into the evolution of next generation communication networks, the role of software-defined technologies, and the future of intelligent network infrastructure. We are truly honored, sir, to have Dr. Sharma with us today. On behalf of organizing committee and all the participants, I extend a warm welcome and express our sincere gratitude and accepting our invitation and taking time to share your valuable knowledge and experiences. So, ladies and gentlemen, please join me in giving a warm round of applause as a welcome to Dr. Ekant Sharma. Over to you, sir.
Hello everyone, good morning. Hope you are able to hear me.
Yes, sir.
Yeah, thank you very much for the invitation and thank you for the kind introduction. And I should thank Dr. Chaya for inviting me for this talk. With this, let me start my talk. I'll be giving my talk for around 25 to 30 minutes, like discussed. And if you have any question in between, please feel free to ask. Don't wait for the end. You can anyway ask me at any point of time. Okay. So let me start. So without going here and there, I'll be talking about what is software-defined architectures. And I'll be showing you some applications of software-defined architectures in the solutions related to 5G and beyond, which will include private 5G, RIS, and even sub-terahertz. So we'll look into some test beds and how they can made intelligent using software-defined architectures. So let us quickly jump into that. So first of all, the question is why exactly the networks need to be software defined? This is the first and fundamental questions that anyone would ask when we talk about we should have a software defined architecture. The first question is why exactly any network need to be software defined? So for that, anyway, suppose for example, if you start with if the network functions are hardware into hardware. So what is the problem? The problem is it's rigid and always it will be expensive to upgrade because every time you have to purchase a new hardware altogether. And like I said, every small change means new hardware. And if you are replacing any hardware, then there will be a long downtime also. It cannot be replaced just like we update an app, right? We have to change the hardware, we have to integrate it once again, and that's why it will lead to a long downtime. So what is the solution? What if the intelligence moves into software instead of having it into hardwired? If we can move that into software, what happened? The same hardware can adapt to new standards, right? Suppose let's say we have any standard we are using, suppose 1.0 for any software. Then if suppose we are to move it to 2.0, right? Then we can use the same hardware by just updating the software. That software-defined architecture allows you. So, for example, software is controlling the radios, core, and services. In 5G, I'm talking about. So there it controls the radios, cores, and services. And it looks like simply updating an app instead of replacing a complete device. For example, we have our phones, right? 4G phones, those who are using, they are able to use 5G network without replacing their 5G phone. If we are using their 5G SIM, right, with 5G SIM. So they have given a thing that, okay, we can connect to the 5G network with 4G SIM. That's why they call it non-standalone, just by giving some software patches. What if they would have hardwired it and they would have not provided a software-defined architecture kind of thing? That is, we would not be able to use it. So it's always good to have a software-defined architecture. That's why. So this shift is enabling faster innovation, flexibility, and real-time optimization. For example, we are able to adapt to new changes. Any security patches that is coming, we can always adapt. Downtime is same because like you're just updating like an app, and we are able to do faster innovation, real-time network optimization. I'll give you some examples also. This is just an idea why it is preferable. It should be preferable to go for software-defined solutions when compared to any hardware counterpart. So it's like shifting from a landline telephone that we earlier used to have to a smartphone. Same hardware, but endless new features that we can get through software updates. That's why I was giving you an example of this. Now, how exactly any software-defined architecture overall would look? I have divided into a pyramid, divided into 3 levels. Obviously, any software-defined architecture, if I'm saying there's a hardware associated with, so there's a hardware infrastructure layers. For example, if I compare with 5G, there's radios, base stations, servers, other storage devices, network storage hardware. So this is the hardware layer. Now comes the software control layer, where we are trying to abstract and virtualize the hardware layers. So there can be multiple software defined architectures. One is software defined radio. So like I work mostly on software defined radios, which is allowing us to decouple hardware from signal processing. So I can do my signal processing on the software side, or maybe on the our CPUs and GPUs, and I can simply use the SDR hardware, USRPs, B210s, and N310s to send my signal over the air. That is one way. Similarly, there is software-defined networking, which is separating the control and data planes. There is a software-defined storage, which abstracts storage management from physical devices. Then there is software-defined compute and virtualization, which allows you to decouple compute from physical servers. Then there is SD-WAN, which virtualizes WAN connections. I'm just given some different software-defined architectures. And for some, SDR may be useful. They may be working on SDRs or SDN and SDRs. Other may be working on SD-WAN and SDP, depending on your areas. But the idea here is we are dividing the hardware layer and software layer. On top of it sits the application, right? For what application you're designing it. You are using some AI. You want to run some AI application on top of it. So you have divided a complete architecture into hardware, software, and application. And you'll see all these things like what I'm saying. I'll show it in our solutions also, that we have developed 3 solutions we have developed. I'll show them. It allows you, like as a faculty, suppose you are a faculty at different colleges, at any college, then it allows you to start your own visualization of the research that you are doing. You can do some research, but you can always use the software-defined network, software-defined architectures to actually create a prototype, small prototype in your lab, and that you can create experiments. You can do your research, patents using those things. So I'll show you some like I said, I work on SDR, so I'll show you some software-defined radio-based test beds with focus on, first one will be on private 5G, where we have developed a robust private 5G network solution. Second would be RIS, which is some of you may be knowing about, which is the reconfigurable intelligent surface, and which is mainly for 6G and beyond. Then sub-terahertz. So where we have created a hardware prototype for sub-terahertz. Sub-terahertz, when I say, we have created solution for 110 to 170 kind of, 180 kind of gigahertz range. That's why I'm calling it as sub-terahertz. This also for 6G and beyond applications. So you divide it into 5G, 6G and beyond. So what is private 5G solution? Like when I say private 5G solution, so simple idea why we had this solution is, when I say private 5G, let me just give you an example what is private 5G. So we all have a phone in our hand. We all use phone, and the phone has a SIM, right? The SIM can come from Airtel, Vodafone Idea, and others, right? Jio. So now what happens? We take our phone, we get a SIM from our network operator, and we insert it, and we start calling and doing video calls and audio calls, downloading, uploading, everything we are able to do. Why? Because our SIM is now, by inserting a SIM on our phone is able to interact with the base station, right? What if we can create our own network, right? We can create our own network. Let's say in your campus, in your department, in your lab, you have your own network. You connect to that network, right? Don't have to connect to the base station. What happens when you connect to the base station? All your data goes to the third party, and if you're doing some patents or for any application, that is not wise. You can create your own private network. That's why we are calling it a private solution. And for that, we have a solution. If you see the box here, the box here shows. Just let me. The box here, if you see, the box here, you see, this is our micro base station. A base station which is of just less than 2 kg, a small box, and when you switch on, it creates a 5G signal. When I say it creates a 5G signal, it acts as a base station, which has complete core, RAM, everything into it. And when it creates a 5G signal, it can we provide a SIM. We have a SIM. We have registered our SIM into this network, and then you can connect your phone just by inserting the SIM into your phone, and you can do all the uplink, downlink data, voice, everything with this. So you have created your own network within a campus. Let's say, for example, that we have done here at IIT Roorkee in our lab. Now, like I said, it's complete custom commercial user. Why I was giving an example of how I want to connect this with software-defined architecture. We have utilized software-defined architecture for creating this box. So we have used SDRs inside this box, which is helping us to modify every time some new release comes from 5G. We update it without changing the hardware. Suppose we provide this, we also sell this hardware through our startup, and we sell it, and anyone wants an update, we just quickly update it without changing the hardware altogether. And then we have also have this orchestrator. What we do is like I said, this software-defined radio solution is made for mostly academia. Most of the labs, what happens, like you all are coming from academia, so I think you will be able to understand what I'm saying. Most of our labs are still running on breadboards, and when we run on breadboards, the students are not learning that much, according to me. Okay, 1 or 2 experiments, 3 experiments, 4 experiments, that is fine. But if we are doing multiple labs only on breadboards, there's not much to learn for students, and that's why they don't feel that much excited. So this kind of solution like this can help students to learn about 5G from scratch. Everything from about 5G they can learn, how exactly network gets established, how exactly network gets connected. So we have created here at IIT Roorkee multiple experiments, 10 to 15 experiments, where the students perform those experiments, and then they understand how exactly overall call flow happens in 5G. That's why this network orchestrator that you see is sitting here. The different specifications corresponding to whether how many users it supports, what kind of antenna configuration we have, what kind of modulation order we support, what kind of throughput we are getting, and all these things depends on, once again, what kind of software-defined radio we are using. Suppose if we are using the software-defined radio like B210s, or we are using, let's say, I've given you an example. If we are using B210s, the coverage would be different. transmit power would be different, the number of antennas supported would be different, and that's why the performance would be different. If you're using high-end N310s or even further X410s or X420s, the support, the benefit that the signal processing can bring will increase. That's why there's a nice gel between the software side and the hardware side. Software cannot do everything by itself; it is limited by hardware. But once the hardware is upgraded, we can always upgrade the software side. And that's why there's an interplay. We have multiple solutions based on B210s, N310s, X410s. Let me go towards the another solution. That is reconfigurable intelligent surface. This is for 6G and beyond. And just let me give you an idea. If suppose someone is not well versed with what is RAS. So RAS is a technology which is relatable to repeaters or relays. If suppose some of you may have heard about what is RAS or what is relays. I hope you guys are able to hear me, right? I just want to have a confirmation.
Yes, sir, you are audible, sir.
Okay.
Audible, sir.
Thank you. So RAS is, like I said, it is just similar to repeater or relay, but with one change. This is completely passive. So when I say completely passive, it does not need a continuous power supply of 230 volt. Like for example, if I want to connect a relay or I want to connect a repeater, I would want a perfect complete power supply all the time. With RAS, we are focusing on a passive device which can be installed anywhere in between base station and user. Suppose let's say user and base station's link is not that good. Suppose user is outside the coverage area of a base station, you can install RAS such that the coverage increases. Suppose let's say another example, suppose user and base station link is weak. The data rate that you are achieving is very less. Once again, you can install an RAS anywhere and then you can increase the data rate. So there are two very nice applications. One to enhance the network coverage, another is to enhance the data rate. This one third application that we also look is blocking the signal. What we do is using RAS, we are not only able to enhance the signal, we are also able to block the signal. Suppose let's say, I'll just give you an example in the current times, like too much war and everything happening and everything has gone digital. Like people are able to detect your tank, your equipments for a long distance. Right? Why? Because they are sending some RF signals, and through that, so that also you can stop by using RAS. We have done that. We have shown that we can make sure that the signals that are coming can be blocked in a particular direction. Suppose that's our tank is sitting at 30 degrees. We can block the signal in that 30 degree. We can create a null zone in that area. That all things can be possible. Yes, someone was saying something.
No, sir.
Any question, audience? Any queries from anyone? No. Please continue.
No, sir, you can continue.
Okay, thank you. So our RAS, like it is a 16 by 16 RAS elements. If you can see, in total 256 number of elements, 16 elements in 16 rows and 16 columns. So 256 element with a center frequency of 3.5 gigahertz, and it supports up to 100 megahertz of bandwidth. So our RAS, like I said, is at 3.5 gigahertz, but multiple people, like once again, if I understand this is a terahertz conclave. So most of the people, or I should say some of the people have started designing their RAS in the range of sub-terahertz frequencies or even higher. So what will happen? The size of the RAS will get smaller, and then you may need more and more number of elements. Like say we have used 256 number of elements, and someone wants to design this, they may design it for, suppose let's say 110 gigahertz or 150 gigahertz, 170 gigahertz, then the size will be lesser, but the number of elements that you can fit will be more. So our RAS is linearly polarized, and it enables signal reflection and precise beam steering. Very important. There are many people that have designed RAS altogether, but most important part is that whether the RAS design is able to reflect the signal properly in different directions, plus whether it is able to provide proper gain. If it is not able to provide proper gain, if it is not reflecting the signal properly, then you will not get the benefit that we have been telling. Similarly, if your RAS is not able to beam steer, suppose it is not able to beam steer according to if the user is moving, it should also change the direction of the reflection. That if you are not able to do, then also it will create a problem. So this is the overall setup. There's a RAS, there's a transmit horn antenna, there's a receive antenna. Why we have used horn antenna? Just to make sure the signal is reflected on the RAS surface, and we are able to show you the prototype. Obviously, in the practical scenario, the horn, it may not be horn antenna, it will be some only antenna, let's say placed on the bases. So it consists of, overall setup consists of RAS panel. This is a panel that we have been talking about. Then there's a controller. Here sits the controller, and the controller software is there. Transmit and receive horn antennas are there, and then this is the software defined radios, USRPs are there, which is sitting inside these boxes. This is the controller that we have designed. Once again, some intelligence should sit, which should be able to tune the RAS elements. Why? Because like I said, we have to do precise beam forming. If we have to do precise beam forming or precise beam shading in different angles, then I need to switch on or switch off different elements of RAS. How it will happen? We are doing this through this controller, RAS controller that we have designed. This is a dashboard. Once again, this is very important. Once again, we have at Roorkee also we have designed multiple experiments or multiple sets, and all these are like, once again, the RAS that we have designed is we have patented that RAS. That is like we have published papers on this, and then we have also selling this to our own company named Mantis Network Private Limited to different academias. Multiple people have purchased, and they are doing their own set of experiments. They're writing papers on top of it, changing the codes and doing research. So overall testbed, what are the applications? Like I said, it is helpful for researchers to design their own algorithms, modify the algorithms, and implement that on real time. Right? They're able to test their wireless communication scenarios. Like I said, I gave you 3 examples, right? When to enhance the coverage, to, for example, enhance the data rate, also to block signal in a particular zone. All those things can lead to, and then they can also integrate this with different use cases that they think that can be possible, like ISAC, Terahertz, anything else. So they can do RAS research on top of it. They can write projects using it. Multiple people have done it through ARG and NRF. They have purchased this while writing their projects. Beamforming experiment they are able to do, and doing all kinds of advanced wireless studies where they want RAS with them. Like I said, it is operating at 3.5 gigahertz, around 3.4 to 3.6 gigahertz, 100 megahertz bandwidth, and other things I've already told. Let me skip this for the sake of time. Then these are the few RAS outdoor management output. I wanted to show you guys. We have done that. Now with this single RAS, the limitation is the coverage. This is 16 by 16 element. The coverage will be limited by the aperture. That's why right now we are able to get a distance of roughly 30 feet or 10 meters. But we have an enhanced version of this where we are using multiple RAS stacked together, where we are able to get more than 100 meters of coverage, extended coverage. I should not say 100 meters coverage, it is extended coverage from RAS. So RAS to receiver distance is 100 to 200 meters. And we have also integrated with our own private 5G box, like I've been telling. So RAS, the beauty of this RAS is it can be integrated with any solution, by 2G, 3G, 4G, 5G, non-cellular standard communication stack or anything. You can integrate it with Wi-Fi. So you can do it because it is a like intelligent reflector which can reflect signal in the direction that you want. Because there's a controller sitting there that you can tune it and you can reflect it. So that's why it is not dependent on which kind of standard we are using on the transmitter side or the receiver side. So we have tested it with 5G base station and our commercial UE. You can see this is a commercial UE here, and this is our 5G box. Very recently, we got some result which is I thought it's a very raw video. I have brought it for you, which is self-controllable RAS. When I say self-controllable RAS, what does it mean? Let me show you. I'll run that video for you. If you see what is happening, we are changing let me just first quickly run that video, then I'll once again quickly play. What is happening? We are changing the direction of the receiver. We have fixed the transmitter, but we are changing the direction of the receiver. And what you are saying is, RAS elements are, if you see, we have changed, the RAS elements are changing. RAS element is automatically able to control its pattern. And if it is, so what is happening? My beams are moving like this. If I'm moving my transmitter, my receiver, my RAS is able to track the receiver. once again, let me just quickly once again run it. Then I think you'll get it. So what is happening? If you see here, I've changed the direction. You can see here or here, the pattern is changing. Once again, I've changed, the pattern change. Pattern change means it is beam steering in different direction. You can see that. And then last two angle, they are almost nearby. So the beam width is slightly big. That's why my pattern did not change. Once again, you can see the pattern is changing. Right. So whenever the beam need to be changed, track, it is happening. You can see that. It's very raw video that we just got a very novel result that we have got. So this is, we are calling it a self-controllable RAS, where based on the receiver direction, my RAS is able to track that receiver in real time. Now, quickly, I'll not go into detail. I'm speaking most of the details. I'm just giving you an idea why software-defined radio-based solution is viable the current for current research or writing projects, or even for lab experiments or BTech, PhD, and MTech students. That was my focus. Now we have also done recently SDR-based sub-terahertz communication test. This project we got from from DOT Department of Telecommunications, where idea was to integrate a complete sub-terahertz based 5G test bed. So let me show you. So the initial part, if you see, what we are doing is we are sending some QPSK or BPSK signal, and here we are using sending at around 170 gigahertz center frequency. You see, what we are doing is we are sending signal QPSK signal, and we are receiving QPSK signal, and that's why we have blocked the signal. If you see what happened, just quickly get the laser pointers. If you see once again, what we are doing, we are sending here. You can see the constellation here, right? BPSK. Now we'll once again change it to QPSK, and we'll block the signal in between. If you'll see that, we'll use our hand to block the. This is a transmit horn antenna. This is the receive horn antenna. We'll block in between, and you'll see that the signal gets stopped. You can see here, it gets blocked, and as soon as hand is removed, it gets received. And here we are transmitting simple text. Hello, yes. Hello, I'm Anuj, transmitting this text to a terahertz decode signal, and we are receiving that signal. Now we have integrated, and once again, why this is important is, you see, we are using simple SDRs. This is simple 2.5 lakh SDR V210. Right, we are using that SDR at a transmitter at the receiver. Obviously, we are also using some up converters and other things. Next, we have integrated this with 5G. Once again, the private 5G, the first thing that we gave you. We've used that private 5G at the transmitter, and then we have designed our own UE receiver at sub-terahertz gigahertz. And then we are utilizing the hardware to transmit 5G signal. So here we are transmitting 5G signal at 170 gigahertz of frequency. We are creating a baseband. Once again, on the software side, we are utilizing hardware just to transmit the signal, and all the processing, all the signal processing we are doing at the transmitter or the receiver. All this hardware, V210s or this hardwares or this hardwares, we are just utilizing for transmission. So that's why we can see that we have divided the hardware and software separately, and then we are that's why in that way we are using the software-defined architecture very properly. And you can see that we are transmitting live video. This is a live video that has been transmitted from receiver at 170 gigahertz of frequency. This very high definition video. Obviously, you can see that anyone can understand the problem with terahertz is sub-terahertz is distance. Distance you have to keep was very, very low. Otherwise, there was always a difficulty in receiving signal. Let's say that sub-terahertz or terahertz frequency will never be used for cellular communication where the distance is large. It will always be used where the distance is smaller, because the application of sub-terahertz will be something like in the server room where we can get rid of the like suppose we have so many network switches and all those things, we can get rid of cables. Suppose right now we use pen drive to transmit information to transmit information from our pen drive to our system or vice versa. We can just have a wireless pen drive where we just keep it nearby and then it can transmit data. So all those applications can be there for sub-terahertz, but according to me, it can never be very near to possible to use sub-terahertz or terahertz, you can say, for cellular communication where the coverage, because we saw that we use the same private frequency stack with some changes, but we are not able to get proper coverage because of, once again, very high frequency range. I think with this, I'll stop. I think I'm on time. Chayaji, you said 11:55. I'm close it at 11:57. So I think I'm done.
Yes, sir. Okay, sir. Over to Dr. Achal.
Yeah, if anyone has any question with respect to any of the SDR solutions, please let me know. We started from 5G, 3.5 gigahertz, then 6G and 6G beyond, and then we went it to sub-terahertz.
So, I have a question that we can use it for drone communication also.
Yeah, anything you can use. See,
Okay.
drone, when you purchase your drone, right?
Yeah.
One thing, we have also integrated our private 5G with drone. We have integrated RES with drone. Even alone drone can have SDR.
Okay.
Right?
Okay.
A software-defined architecture where you can place hardware on top of it, and then you can do your software signal processing. We have done that also.
Okay.
Thank
Any
you very much, sir.
Yeah, please. Someone was saying something.
Yeah. Any question from the audience? So with this, I would like to thank Dr. Ekant Sharma for giving us an insight about today's topic. So the key takeaway from this topic that he has talked about the significant part of lecture focused on the test boards, which served as an experimental platform for validating new communication protocols. And Dr. Ekant Sharma is also founder of a company, and that gives us a motivation that we can also work in this direction. And his product, the products are very new eyes to us, and we have never seen this type of capabilities in this environment. So on behalf of JSS University and on behalf of Department of Electronics and Communication, I would like to thank Dr. Ekant Sharma for giving his time. And with this, we will also like to share a token of appreciation.
Thank you very much, Dr. Bharat. Thank you very much.
Thank you so much, sir.
Thank you.
Thank you, sir.
Thank you, everyone. Yeah.
Thanks.
Thank you, everyone. We will now break for tea, and next technical session will resume at 12:30 p.m. So everyone, we take tea break. Thank you. And we resume at 12:30 p.m. Please be there for the next session. Kindly reassemble on time. Thank you.
All are requested to be there. Link is on. Link will be on. And we again join the session at 12:30. हेलो हेलो नहीं आ रहा ओके
मेरा ही डिस्कनेक्टेड होगा, मैंने बंद कर दिया ना।
वाह मैडम वाह
बोलिए मैडम।
यस
Yes, yes, you are audible, ma'am.
ओके
Welcome back, everyone. We now resume our summit with another exciting technical session featuring our distinguished academician and researcher in the field of advanced wireless communication. I would like to invite Dr. Pooja Pandey to kindly come forward and introduce our distinguished guest to the audience. Over to you, ma'am.
It is my pleasure to introduce our distinguished guest speaker, Dr. Jitendra Prajapati, Associate Professor in the Department of Electrical Engineering at Shivnadar Institution of Eminence, Greater Noida. Dr. Prajapati received his PhD from IIT Guwahati in 2018 and previously served as an assistant professor at NIT Sikkim. Hertz and millimeter wave antennas, photoconductive and photomixing antennas, orbital angular momentum antennas, reconfigurable intelligent surface technologies. He has published over 20 research articles in reputed international journals and more than 25 conference papers. He has also successfully completed sponsored research projects funded by organizations such as DRDO and has guided research at the doctoral and postgraduate levels. In recognition of his outstanding research contributions, he has received the prestigious IETE K.S. Krishnan Memorial Award. Please join me in extending a warm welcome to Dr. Jitendra Prajapati. We are honored to have him with us today and look forward to an insightful and inspiring session. Over to you, sir.
Thank you, Dr. Pooja. Thank you for inviting me and giving a kind introduction. And thanks to Dr. Chaya and Dr. Jyotishri for making this possible. So let me share my screen first. I hope my screen is visible. Is my screen visible?
Yes, sir.
Okay. Okay, so I'll start about terahertz communication. So from the recent few years, we hear a lot about terahertz everywhere it is there, but we don't see any commercialized or many commercialized product in that particular domain. So this particular talk will be about overview of the terahertz communication, its advantage and applicability over different application sectors, as well as I'll also discuss that why it is not much commercialized yet and what could be the future aspect in this particular domain. So when we talk about the terahertz, we are talking about the frequency range which varies between 100 gigahertz to 10 terahertz. Sometimes we also classify it in two different domain. One is sub terahertz and terahertz. Sub terahertz is for 100 gigahertz to 1 terahertz, and more than 1 terahertz frequency we call terahertz only. So why this particular frequency band is so people are so much interested about these frequencies. So these frequencies have certain unique characteristics which makes it very useful for many applications, like these frequencies has very low photon energy which can be directly used in the biomedical sectors. It has several materials have their unique fingerprint in these frequency bands. So you can, based on the fingerprint, we can easily figure out that which particular material is present. And these frequencies are also useful when we are checking about the material, because some materials are transparent to these frequencies, some materials are completely opaque to these, and these frequencies are strongly absorbed by the water molecules, which can be used in the different application. Why it is so much useful? Because see, in the lower frequency regime, which is microwave frequency regime, it is completely crowded, too many application at the single frequency, so we do not get too much bandwidth for certain applications, so achieving high data rate is not that much possible. Whereas the terahertz band, it is completely open, not many applications are being used as of now, so we can have a very large band to use for a certain application here, and due to very large band we can achieve very high rate of data communication here. So as we say about that, these frequencies are very useful for different application. Let's see about what kind of application these frequencies can be used. So when we are talking about the biomedical related application, we can use the property of the terahertz, that it is strongly absorbed by the water molecules. So I mean, when we are using it for the imaging application in the biomedical sector, it can give us more it can give us high resolution images and more in-depth knowledge about the what kind of disease or what kind of things are there present in that particular thing, that particular biological tissue. So it can be used in the cancer detection, because those cancer tissues are very dry compared to your normal tissues. So based on the water percentage, we can figure out whether it is a normal tissue or a cancer tissue. Also, it can be used for non-invasive application, imaging application like your dental oral health care. It can be used for the biomolecule or DNA analysis. It can also be used for the pathogen detection, because those will have their unique signature for these particular frequencies. Similarly, if we look about the industrial application, so wherever we want to use a non-invasive kind of non-destructive kind of imaging, we can easily use terahertz frequencies, and we can get the required information for whatever purpose we are going to use it. Like biomedical sectors, when we want to check that whatever pill has been made, whether the whatever pill has been made, whether it has the same drug composition or not, what it has been decided prior. So without breaking that pill, we can check that what kind of component, what is the percentage of different drugs in that particular thing. So it can be applied over the whole batch of medicine without breaking that particular pill. Similarly, it can be used for the micro or nano gap break which comes into the materials. It can be easily used to detect those kind of cracks in it, and then whatever feasible thing is there to fill those gaps, that can be done. It can be also used for the agriculture area, where it can be used for the checking in the quality of the seeds. It can be used for the soil inspection. It can be used for the crop monitoring thing. It can be also used to detect that whether there is any insect present in that particular crop or not, disease detection and all, everything it can be used. Similarly, it can be also used for the defense sector, where it can be used for the scanning application to check that if any particular person is hiding anything, any particular chemical component or any particular kind of weapon, it can be used for that also. For the like normal frequency, which can be used for the communication things, Terahertz waves can also be used for the communication in the defense sector. But with some limitations are there, that I'll be discussing, that what kind of limitations are there, why it is not so much applied as of now, and what could be the future of things. So it can be used for the communication. Terahertz can be easily incorporated with the existing technologies and can complete the communication, high data rate and high bandwidth communication. So I mean, the overall terahertz domain has a lot of application, but due to certain limitation, we are not able to use it properly as of now. And what are those limitations? As of now, whatever terahertz sources or terahertz detectors are there, those are very costly in nature. And if you want to apply it for certain application, the overall setup will be very, very costly. So the cost is main thing in any particular application. When you go for like industrial application, or you are making any particular system, if it is very costly, no one is going to buy that. So as of now, the terahertz systems are very costly. The detection in source side, the source are costly, not that much efficient, limited sources are there. Similarly, in the detector side, not many detectors are there, and also the efficiency is a question there. And then what kind of communication we are doing, whether we are able to extract the complete information or not, because the non-availability of the very efficient terahertz receivers. Then these terahertz wave are strongly absorbed by the water vapors or water droplets in between. So when you are using terahertz waves for the wireless communication or any application where there is a transmission of these waves in the wireless media, then it is a very complex system, because you will not be able to cover very large distances. And when you are not able to cover the large distances, you are putting things closely, very closely, so you will not be able to complete the application requirement. With the apart from the water vapor, there is heavy path loss happening for these frequencies. So long range communication is not possible here for these things. As I have already said, that these particular waves are transparent to certain material and opaque to certain material. So what happens that most of the your building structures, your terahertz wave will not be able to penetrate. So when you want to do a communication, then there is no line of sight in between, so you will not be able to complete the communication channel, and you will not be able to receive the whatever information is being sent from the transmitter side. When we talk about the sources or the receiver, they are based on certain material. So here, those materials are not some ready-made semiconductor materials or easily available materials which can be used to fabricate or to make those transmitter or receivers. So those materials are very costly in nature. So when the material is costly, the overall cost of the sources and the receiver will be costly. Though the bandwidth and data rate at this particular terahertz band is very high theoretically, but achieving those bandwidth is not, I mean, as of now, whatever we have got is not that much high. We'll see some studies which has been published till now, that what is the highest rate, data rate they have achieved, and what is the distance they have communicated to receive the signal. Then there is a very complex integration of the system, because terahertz systems is completely different whatever we have right now, the 5G and 4G system. So the interoperability will be difficult as of now. So it is difficult to have a complete terahertz system which can be used for certain application. The cost is very high, so it is not that mature as of now. Okay. And also, when we want to make something new, we need to to see that whatever existing technology is there, how the new technology is better than the existing technology. So as of now, if you compare the terahertz technology with the microwave technology or the optical technology, the terahertz technology is premature, and it is not up to the mark whatever it should be compared to other technologies, whatever existing technologies are there for different applications. So as the talk is little bit related to defense technology, so I'll just discuss a bit about the defense technology. So in the defense technology, when we talk about the communication thing, here everything is connected with everything, because we cannot have any time instant where the connection is break. So here in the defense technology, your different kind of communication setups are interlinked, like your satellite communication is connected with the ground station, as well as directly it is connected with some other things are also. Your command center is controlling the communication between your all kind of defense vehicle, maybe your ground vehicle, maybe air vehicle, your fighter planes, or your early warning system, whatever are there. Also your ground troops are connected in real time, so you cannot have delay in between communication or break of the communication channel. So in the defense, you need to be sure that all the communication channel are working fine. If you are not able to connect in one way, you are able to connect in the other way, so that you can complete the communication and real time data transmission or data sharing can happen. So how terahertz can be useful here? So if we see the before that, what kind of requirements are there for the defense communication? So in the defense communication, first thing is your security, that whatever data you are sending, that should be highly secure data, and it should not be intercepted by any other one who is not in that particular data communication network. So security should be there, low probability of detection should be there, and interception should not be there at all. And also the data communication, whatever is happening, that should be very fast in nature. There should not be any latency. The data rate should be very high, and for as we are including many things into it in one particular system, the spectrum availability should be very large, means that you should have very wide bandwidth, so that you can provide the required bandwidth for each and every communication channel. You'll be sending video data, you'll be sending audio data, so they will require huge bandwidth, huge frequency availability. So those things should be there. And also for the communication, not just for the defense communication, in any particular communication, we see that the coverage distance should be very large. Okay, and the data, the whatever signal you are sending, the decay in that power level of the signal should be small, so that you can cover very large distances. Doesn't matter what kind of environmental condition is there, your data connectivity should be there. Very harsh condition or in ideal condition, your data connectivity should be there always. Then only you will be having a proper communication network. So these are the requirement for the defense network side, and how the terahertz can fulfill some of the requirement, not all of the requirements. First, the requirement is for the high bandwidth. So terahertz band is completely vacant. You can have as much as bandwidth you want to get, you can use it for your communication network. Then it should be able to get connected with different kind of system, maybe local area network, maybe your satellite link or anything. So terahertz can be easily used for that particular purpose. There should be high data rate. So at terahertz frequencies, due to availability of very wide bandwidth, we can achieve high data rate here. Then your system should be compact, because when you are giving it to ground troops, so they will not be able to carry very large system with them, so that they can communicate with the command center, or they can communicate with the nearby system, whatever is there. So as terahertz frequencies are very high, so as we know that the component size is inversely proportional to the frequency. When the frequency goes high, your component size will be very small. So as the component size at these frequencies are very small, so you can include more and more component in your chip, and you can make a system. So overall system size will not be that big here. So at the terahertz, the system size is compact, and it can be used for the handhold system. It can be used for the mobile platform or anything. It can be easily done. Now, coming to the detectability and interceptability of the terahertz communication network. So here at the terahertz, as we know that there is a huge path loss happening in between your transmitter and receiver. So instead of sending the data over a wide beamwidth channel, what we are doing, we are making antenna system such that it can provide you a very narrow beamwidth. So very narrow beamwidth system, and as your size of the antenna is very small, you can put as many as antenna you want to put there. So your massive MIMO kind of structure you can have. And also these antennas are providing you a very narrow beamwidth radiation pattern. So when the narrow beamwidth radiation pattern is there, which is directly focused to the receiver side, so the detection probability from the any unwanted user is very less. Okay, and then over that we can also put some cryptography or security system, so that even, I mean, in narrow beamwidth case also, if someone is able to receive that somehow, if the unwanted user is able to receive that, they will not able to crack the overall information what we want to send from the source to receiver side. Then one more problem with the terahertz wave is that it is highly dependent on the weather condition. So when the weather condition is changing, your coverage area will be reducing with that. But if in ideal case scenario, we can use it for the communication over the longer distances also. Interoperability and heterogeneous network integration is possible with the terahertz technology. Not as of now, but in future it may be able to complete those requirements also. Now, the overall problem with the terahertz wave, which is limiting its uses as of now, so the path loss, drastic path loss because of the water vapors present in the environment, your free space, blockage by the materials, and then limited line of sight, because when you are sending a narrow beam signal to the receiver side, and because of very small wavelength of the signal, so you will not be having reflected, or you will not be having refracted signals or reflected signal that much. And also because of the environmental condition, even if you have some reflected or refracted signal, those will not be able to travel to the desired point where it can be received and can be decoded whatever data has been sent. Now, we are saying that we will be using the very narrow beam with antennas to send the transmission. Now, when we are having very narrow beam with signals, radiation pattern, then the receiver side, the receiver should be exactly focused or aligned with the narrow beam width to receive the signal. Otherwise, it won't be able to receive the signal also. So the beam alignment complexities will be also there. Then the hardware difficulties, like your sources are not that efficient, your receivers are not that efficient. So sending the signal, and then due to less efficiency, your signal power level will be very small, so coverage distance is also going to be very small. So when we want to use it for the very large network in the free space communication, open environment communication, so as of now it is not possible, and you'll not be able to achieve very large coverage area or large distance communication here. Moreover, though we have some hardware, the software, the transmitter and the receiver, but very limited commercial availability because they are very costly. They require certain material which are not easily fabricated. So these things are limiting the overall application of the terahertz system for any particular application, not just the communication, any particular application. Now, few studies has been done for the your free space communication for the terahertz wave, and till 560 gigahertz, till 560 gigahertz researchers have used, and they have shown that what kind of capability it has, what kind of data rate we can achieve, what distance we can cover using these frequencies. So here we see that at 120 gigahertz, which uses your hemp based transmitter sources, transceiver sources, they have achieved 5,800 meter as a distance between your transmitter and receiver, whereas for the same the data rate was very low, 10 Gbps. If we see with respect to data rate, so the researcher have achieved till 200 Gbps data rate over a distance of 0.5 meter only. So when the distance is large, Your data rate is very small. When the distance is very small, your data rate is researchers have tried different kind of modulation scheme also, and they try to increase the overall data rate for that particular communication. They have used ASK, PSK, QPSK, QAM based signal, and many other techniques they have tried to incorporate to complete the terahertz communication network. One more thing here, we should note that whatever terahertz sources they have used, they are mainly based on the solid state devices sources, mean the semiconductor devices. They have used photodiode, they have used resonant turning diode, they have used hem devices, highly electron mobility transistor. They have used CMOS based devices to achieve these high data rates or longer distance communication. Okay, they are till now they have not gone to exactly terahertz. They are in sub terahertz regime, and this can be used for to complete the communication application with certain limitation. Now here we have whatever sources are being used, they are based on solid state devices only. But for the terahertz system, we do not have only solid state based devices. We have different other devices also which can generate high power also or high frequency. So if we classify the terahertz sources to be used in any particular application, maybe communication, maybe industrial application or biomedical application, we can classify it into 4 different domains. One is your vacuum tube based sources, another is your solid state electronic based sources, then only laser based sources, and then optoelectronic based sources. These sources, they have some pros, some cons. So if you go for the vacuum based tube based devices, we have backward wave oscillator, gyrotron, klystron, synchrotron. All these vacuum based or vacuum tube based technologies, the sources are there. So these sources can generate very high power. They can generate up to 1 mega or 100 megawatt power. But the frequency what they can achieve is limited to lower side only. So they can generate frequency between 100 to 300 gigahertz with very high power output. But when we say very high output power, it doesn't mean that they are very high efficient. The efficiency is still not that much big. For these sources, the efficiency reaches up to 20 to 25%, not beyond that. So efficiency is still small, but the power output, because we are putting too much input power, the power output is in megawatt range. But the issues with these sources are that these sources are bulky in nature. They require external magnetic field, they require cooling technique also. So the structure is large. So when we want to make a compact system, we cannot use these sources to make a compact communication system or compact system for any particular application. When we move to solid state electronic devices, we have frequency multiplier, resonant tunneling diode, we have impact, HEMT, and gun diode, CMOS based. Multiple kind of devices are there which can be used to generate the terahertz radiation. So these sources are compact in nature. They can generate a relatively high power, not very high power. So they can go up to 10 to 20 milliwatt power output can be there, but efficiency is again around 20 to 30%, not more than that. So efficiency is still low, but they can achieve from lower to higher frequency range. They can go from 100 gigahertz to 1.8 or to around 2 terahertz. This much frequency band can be covered by using these solid state electronic sources. Okay. Then laser-based sources, where the terahertz is being generated by using only laser sources. So here we can have quantum cascade laser, gas laser. We can have optical rectification, where the laser is being shine on a semiconductor material, and second order rectification will happen to generate the terahertz sources. So these sources requires, again, the limitation is that these sources require very high power. The output is very low, efficiency is very small, and they can generate the frequency range what they can cover. They can cover very high range of the frequency. They can go from 100 gigahertz to even 15 terahertz or something like that, based on certain lasers only. So the frequency, with respect to frequency, it can cover a larger band, but the output power is very limited. And they are, again, the overall source system will be bulky because they require cooling technology. They require some, the overall optical setup with it. Then we have optoelectronic sources, which is a combination of semiconductor and the laser source. So optoelectronic sources require femtosecond lasers, they required semiconductor material, but not the normal semiconductor material. They required specialized made semiconductor material. So when we talk about the semiconductor material, generally we do not want that there should be any defect in those semiconductor material. For solid state electronic devices, we want a defect-free semiconductor material. Whereas for the optoelectronic sources, we need a semiconductor material which has very high defects. Means that your it should be defect level should be around 10 to the power 17 to 10 to the power 19 centimeter per centimeter cube. Those should be, we call those defects are also called as a trap. So trap density should be very high, so that the overall carrier lifetime of that semiconductor material should be very small. So here the main phenomena is that your semiconductor carrier lifetime is small, and your laser, what you are shining on those materials, are turn on for very small time, femtosecond time only. So the ultra fast radiation will happen from these sources. So these sources are two types of sources. One is your photoconductive and one is your photomixing. Photoconductive uses one laser, whereas photomixing uses two lasers. So the benefit of these sources over all other sources is that they can achieve very high frequency. They can go up to 6 or 7 terahertz also. The frequency they can achieve high. The power level is small, that is a drawback. But the benefit is that that same source can be used as a receiver. So you do not need to, like your normal antenna can be used as a transmitter and receiver. But when we see for the terahertz, all the vacuum based sources or solid electron or laser based sources, they do not do that. Your source is different, your receiver is different. Whereas in optoelectronics, you can use the same fabricated source or same design for the transmitter as well as the receiver. Now in the receiver side, again, we have multiple kind of receiver. It can be divided between the coherent and the optoelectronic based sources and incoherent sources. So coherent may we have mixers, Schottky barrier diode based mixers. We have hot electron bolometer mixers. We have semiconductor insulator superconductor mixers. We have highly electron mobility transistors. Okay, so these are under coherent heterodyne receiver kind of thing. So what happens, they required a cooling system with them to achieve whatever operation we are going to use them for. Then in optoelectronics, we have photoconductive antenna and sampling cluster. Okay, EO sampling cluster. So photoconductive antenna, as I said, that it can be a transmitter, it can be a receiver, but the efficiency is very low. So the overall, when you compare with the other system, your system overall efficiency will be very low. Then your direct thermal based detectors, we have bolometer, we have Gole cell, we have pyroelectric receivers. So the system response is slow here, and they are sometimes bulky in nature, and sometimes they also need cooling technology to complete the application. So if we see in the terahertz domain, as of now, the current, based on the current status, there is a huge opportunities to work on terahertz technology, different sector, not specific to one sector. So you can work on the device side, maybe transmitter, maybe receiver, as well as the other component which will be used to complete the transceiver system. We can work on the channel propagation, though we are not able to remove or reduce the overall behavior of the wave. That terahertz wave is getting absorbed by the water molecules in the free space media, but somehow we can use the techniques which can provide you the combination which can give you larger coverage distance without losing the power much in between the transmitter and receiver. Then at the system level also, we can design the complete back end and front end system, okay, for the terahertz system. We can include the AI ML technology which is coming into each and every area, so it cannot be differentiated with that. So we can include the AI technology also to enhance the overall efficiency of the system, as the calculation method and everything, so that not much power is getting wasted into the pre-processing or post-processing of the data. Then to increase the security and to enhance the reliability, we can include the cryptography techniques so that it cannot be getting intercepted by the unwanted user. And then based on the application, there could be certain other specific requirements which can be taken for the research. So as of now, whatever we have seen, that the major limitation of the terahertz system for the communication is that whatever sources and receiver we are using, those are not that much efficient. So somehow, if we start working on the sources, any one of these sources where we can enhance the overall efficiency of the system. Like here, if I say that I mentioned that the vacuum tubes and solid state electronic sources, they have 10 to 20% efficiency, whereas the optoelectronic based sources, they have even lesser than that. The efficiency is 0.01%. So you are putting too much power, but you are getting very small power because of the system configuration, the component which are involved in making that particular source. So somehow, if we start working toward the efficiency enhancement of the system, then the coverage range problem which is coming into the terahertz technology, it can be somehow reduced, because we cannot completely make it that efficient so that we can go for the very large distance communication, but we can improve it whatever is the current status compared to that. So here at the Srinagar University, we are working on that side only. So we are working on the terahertz sources, mainly on the optoelectronic side, where we want to enhance the overall efficiency of the photoconductive and photomixing antennas. And also, apart from that, for the lower frequency microwave regime, we are working on the OM antennas, RIS system, SAR satellite for satellite application, on different component for the lower frequency. For the higher frequency, we are not doing that much. We are working on the source only for the terahertz system. These were the references I have taken to gather these informations. Okay. Okay. So any question we can discuss? If there is any question, we can discuss that.
I think, sir, there is no question.
Okay.
Thank you, sir. Your session has provided our students and faculty with valuable insights into this rapidly evolving terahertz technology and has motivated to explore new directions in research and innovation. As a token of sincere appreciation on behalf of the entire Department of Electronics and Communication Engineering, I would like to present this memento to our esteemed guest, Dr. Jitendra Prajapati, with
Thank
a
you.
heartfelt
Thank you.
gratitude and best wishes.
Thank you. Thank you, everyone.
Once again, thank you, sir, for taking the time to be with us today and for sharing your knowledge and experience. Thank you, sir.
Thank you. Thank you.
Thank you, ma'am. Ladies and gentlemen, we shall now break for lunch. The afternoon session will commence promptly at 2:30 p.m. So thank you, and please join for the after lunch session. वो नहीं बना रखा होस्ट, आपको होस्ट नहीं बना रखा। को होस्ट पार्टिसिपेशन का सर्टिफिकेट देख लिया, बना दिया। Welcome back. One of the most anticipated sessions of today's summit is the panel discussion. And for today's panel discussion, we are privileged to have with us Mr. Shashi Shekhar Pandey as government representative, Professor Ekant Sharma as Terahertz communication researcher, Mr. Lakshmiya P as government representative, Mr. Sagar LNU as AI and 6G research expert, and Professor Jitendra Prajapati as defense communication expert. I now invite all our esteemed panelists, and I also request Dr. Chaya Dallela to facilitate the panel discussion. Over to you, ma'am.
Yes. Just a minute. I, Dr. Chaya Dallela, as moderator, welcome to our distinguished guest for panel discussion on Terahertz communication, shaping the future of 6G, defense and beyond. As the world moves beyond 5G, terahertz communication is emerging as a transformative technology, promising unprecedented data rates, ultra-low latency, and revolutionary applications across communications, sensing, healthcare, industry, and national defense. Today, we'll explore the opportunity, challenges, and roadmap for realizing the terahertz-enabled 6G ecosystem with our panelists. To you, Mr. Shashi Shekhar Pandey, as a government policy representative, what is your opinion about is terahertz communication ready for large-scale deployment, or are we still in research phase? We are interested to know your opinion, sir.
Thank you very much. Ma'am, as I have presented in my morning session, like terahertz communication has a lot of challenges. As far as it has a lot of opportunities in terms of higher bandwidth, high bit rate, and then this terabit communication is possible. But the challenges are still in front of us, and I believe the researchers are in testing stage of its deployment. So, though it has the potential to make internet 100 to 1,000 times much faster, but researchers are still solving those challenges, technological challenges, and like the challenges that I have mentioned, like the high propagation loss, limited coverage, blockage, even hardware complexity, which will come when we are processing this terahertz frequencies, and even the energy consumption. So all these challenges are still under research phase for their solutions. So I think, if we remember early days of UPI, so there were only few users, but over a period of time, all now it has become part and parcel of our life. Similarly, I believe around 2023, we may see limited uses of this terahertz applications, probably in hospitals, labs, or even in air force, or in a very controlled environment. But in a longer run, terahertz is future, and today still in under development stage. So this is what
Thank
I
you very much. Thank you very much. One question is coming in chat. Any question from the audience? Please speak on your video and please speak. Any questions from audience? Okay, fine. Sir, how can academia contribute more effectively for the national 6G missions?
As I mentioned, like academia has a pivotal role to play in 6G vision document. Even the first phase, which was the incubation, like initiation phase, ideation phase, basically, wherein the ideas which can solve the problems and which can really be a candidate technology for 6G adoption will definitely come from academia. So, just like as an Indian engineer, we have seen the development of UPI, Aadhaar, even complex missions like Chandrayaan. Similarly, so I believe today's student can really help in building tomorrow's 6G technologies. So universities should focus on research. They should build working models and promote innovations through their students and encourage startups. Like we have good startup establishment in all IITs, in all universities. So those startup incubation should be pushed up, and we should focus on trained, skilled engineers and scientists who are well versed with the technology. So work together with industry and government to achieve the 6G vision of government. So thus the future of 6G will be built in our classrooms and laboratories. And the Bharat 6G vision of Atmanirbhar Bharat in 6G domain could be achieved with active contribution of academia. That's
Means collaboration is the only means. Academia with industry collaboration is the only means for the implementation of the early 6G.
yes, ma'am. And for that only, that 10,000 crores fund has also been early fund has been proposed in 10 years phase. So academia is the most pivotal element for this.
Thank you very much. Sir, in 1 minute, please share your vision. What will the most transformative impact of terahertz communication on society by 2035? As you told, you discussed that it will be implemented by 2035. So, what will the most transformative impact on the society?
And the terahertz communication will not just provide faster internet, but I believe it will make our lives smarter and more connected. Smarter in sense like it will be strengthened with the inbuilt AI, so it will definitely make our life smarter. And like we can imagine that a doctor sitting in AIMS Delhi is treating a patient in Andaman Nicobar or in the far-flung areas of Arunachal Pradesh. Even driverless buses moving safely on Noida Delhi highway. So these kind of things will be a reality. So I believe by 2035, 6G will help create a more connected, inclusive, intelligent, and prosperous India, where technology benefits every citizen and bridging of the digital divide. So this is what I feel, ma'am.
Thank you very much, sir. Thank you very much. Now,
Ma'am, I have one question. Madam, I have one question to ask.
Please.
Yes, ma'am, please ask your question.
So my question is, good afternoon, sir. This is Dr. Monica Malik from EC Department, JSS University. Sir, I have one question. How can interdisciplinary research accelerate 6G development? Like how we can connect the interdisciplinary with 6G?
Very good question, ma'am. Actually, as I mentioned in the previous answer, contribution of academia. So already a fund, 10,000 crore fund has been proposed, wherein interdisciplinary research are a must, which will come up with different solutions, which can become a candidate technology in 6G. So at this stage, uh, we must focus more on research and patent side, so that those patents may be accepted as a candidate technology in 6G. And once they got accepted, they will get a worldwide recognition, and the whole world has to implement it. has to like, commercialize it. So we can be, as I mentioned, we can be from side of 6G consumer. We will be the deliverers and we will be the manufacturer of the or supplier of the equipment in the whole world. So interdisciplinary participation is really crucial at this phase. Anything else?
Yes. Thank you, sir.
Thank you. Any other question?
Sir, I also have one question.
Yeah.
Sir, it is not really from technology point of view, but health point of view.
Please, ma'am.
See, I work in health domain, sir. So I'm little concerned when we are working with such high range of frequencies in gigahertz. Will there be any impact on the human health and the animal health? Is the government considering these impacts when they are considering to shift towards 6G technology, or they are not considered at all? Or it's just technology and moving towards technology and not about the animals or human health?
Okay. What I got, like you're talking whether the government is primarily focused towards the technological development and not considering the human and animal health, like living beings health concern. Is it the question?
It is. Yes, sir. Yes, sir.
Okay, okay. So first of all, I'd like to convey during my presentation, like I have shared that circle around the circle there were four
Five.
guiding principles. So there was sustainable development. Even in Bharat 6G vision document also we are focused towards achieving sustainable development goals, which has been the UN already identified those. So the sustainable development goal already covers that we have to have comply all the norms which are in good in good favor, considering all the health concerns, etc. But beside this thing, I would like to mention one thing in today's scenario as well. In India, the EMF norms what India is complying is 10 times stricter than other countries. So that clearly conveys the government stand. Wherever any health hazard or any health hazard or any concern comes, so our behavior will be rather more stricter. And we, as a Department of Telecom, we are complying and we are completely checking whether any tower is radiating more than the prescribed norm or not. So from rest of the world, we already have 10 times much stronger rules as far as health hazards are concerned. And since 6G standards are not yet formalized, they will be formalized by ITU like 2030. So under that framework, whatever health hazard concerns, whatever EMF radiation norms or other things will come, so we will definitely, we will have India may have their own much stronger and stringent norms. So in that way, I once again want to apprise that in India, EMF norms and other things are in a much stricter position, and everything is nowadays remotely controlled, like managed. So it is not possible that anyone is reaching the limit. So we are completely taking care of all the health concerns which are known, right? So I hope I was able to answer your question.
Yes, sir. Thank you, sir.
Thank you. Thank you very much. Now, this is, I move to Mr. Lakshman P. as a policy representative. What is your opinion, sir, that is India ready for terahertz and 6G leadership?
Uh, Hi, ma'am. Yes, ma'am. See, until 4G, India was a technology adapter, but 5G, we contributed some of the patents, some of the 3GPP contribution to the 5G. Now, India has already formed released Bharat 6G vision statement by in 2023, and then they formed a 6G alliance, Bharat 6G alliance. And based on the statement, they have prepared a DPR, detailed project report, which says that the vision of the DPR says facilitate India's effort to ensure at least 10% of the 6G patents by 2030, and then establishing multi-institutional test beds that supports peace standard and standards-based research and prototyping. These are all actually in the morning session Pandey sir mentioned, and again I'm repeating. Also, drive India-specific 6G applications in healthcare, agriculture, and logistic educations, and disaster management and smart cities aligned with sustainable development goals. And so, and building a skilled human capital base of engineers, researchers, PhD scholars, and standardization experts in 6G technology to sustain long-term relationship. So when it comes to human resource development, they were targeting 100 plus PhD students, 500 plus research papers, 200 plus patents, skilled telecom researchers and entrepreneurs. So by 2030, the expectation was 10,000 plus 6G patents from India. So, and then significant contributions to 3GPP release 2021 and ITU IMT 2030. And I'll tell you, I am the part of one of the networking national working group 12. This is a study group 12, which is focusing on performance, quality of service, and quality of experience. So India has already actually ITU accepted India's contributions in this study group. So work is progressing towards 6G technologies and and one more thing, see, already pre-6G trials started in IIT Hyderabad under the supervision of Professor Kiran Kuchi. And so along with that, see, government is encouraging academics, startups by providing funding through TTDF schemes. And then Government of India has already established 100 5G test labs. Those are all actually basis for 6G research. So going through all the things, then if you execute the plan as per the DPR, Bharat 6G DPR, so India can become the leader, one of the leaders in this 6G technologies by 2030.
Thank you, sir. Sir, one more input I would like to get from you: that how can universities establish terahertz research laboratories?
Yes, ma'am. Actually, it is very much possible, but the only thing is concern is funding. So this high frequency capital equipments are costly. I'll tell you actually what TTDF see under TTDF, DOT sponsors three terrorized communication. One is National 6G terrorized testbed. There are four consortium members: Samir, along with the Samir, IIT Madras, and IIT Patna, and IIT Guwahati. They formed National 6G Terahertz testbed, TDDF funded in that. And in that, actually, CDOT is an implementation agency. So we are monitoring that progress. And along with that, and we have TDDF funded one IIT Roorkee Professor Darshak Bhatt. He is also working on Terahertz communications, and then IIT Delhi also working on Terahertz communications. So Terahertz communication labs are available, they are establishing, and then research is going on. So if at all universities wants to establish their own laboratories, they can approach Government of India funding, and then they can collaborate with the existing Terahertz laboratories, and then they can get the help from them. And then see, after establishing 6G terahertz test bed in IMC 2025, IIT Madras showcased one high throughput links, which is around 51.2 Gbps in the frequency of 270 gigahertz. So that's research is already going on. And then in one more thing I'll tell you, in IIT Roorkee, there is a specialized group called, their group is working on terahertz and sensing communications. So
Okay.
if at all you want to establish your own laboratory in terahertz, you can collaborate with these universities. You can get the, you can approach Government of India for funding, and then it is very much possible.
Okay. Thank you very much, sir. Thank you. Now it's time to take the inputs from AI and 6G research expert, Mr. Sagar LMU. Sir, As plane, Jitin. AI in managing terahertz enabled 6G networks. Sagar sir is there?
Yeah. Am I audible?
Yes, sir. Sir, thanks for joining. Sir, just give your opinion that how important is AI in managing terahertz enabled 6G networks?
Yeah. Thanks, Chairman, for the opportunity. So, to begin with, the main challenge which we have with terahertz communications, like one of the main problem which we are facing with terahertz communication is channel modeling. So as we all know, right, most of the channel band, I mean frequencies which we work on are falls in the far field zone. So when we do the far field zone, the waves propagate. I mean the wave propagation is like vertical planes after merging. And in that case, you can easily, and you can modulate it like, I mean, you can model it slightly easier way. But when it comes to the near field, which get extended in the range of some kilometers, when your frequency goes in the range of like 100 gigahertz or like 300 gigahertz or those range. So in that case, your near field becomes in the range of like 1 kilometer. And since 1 kilometer is a big range for a node B, especially for terahertz, because the terahertz itself, is hampered by the noise, environmental noise, and very heavy path loss. So in that case, our terahertz communication, all the channels will be mostly falling in the near field zone. Now, as soon as we move to near field zone, the communication concepts and the calculations becomes very tricky and very complicated. Now AI comes in the game there. It can handle this kind of non-linear problems, I think, more effectively compared to what we have, that baseband signal processing which we do. So this is one of the use cases which AI can target. Beside that, beam management. So if you see in current, even from millimeter wave, if you see, we have like more than like 60, 50, 60 beams kind of concepts. And then tracking everyone, checking the cell condition of that, then taking a call which beam to switch on. It's always been challenging with the millimeter wave. And it is going to be more severe when the terahertz comes in the play. So with these all problems, I think terahertz AI will play a key role, especially in the beam prediction and this non-linearity handling. It will be much needed thing to move ahead with the terahertz communication. So yeah, this is what I have on this point.
Thank you, sir. Sir, in 1 minute, please share your vision in brief that what will the most transformative impact of terahertz communication on society by 2035? As we were discussing that it will be implemented by 2030 or 35 as Government of India wanted to do.
So let me give you an example in a slightly different way. So for example, we all know sensing is one of the best, one of the most important use cases of 6G, right? And then in sensing, we need to do a lot of data handling, right? Because for sensing, so for example, if somebody is, the health monitoring is one of the use cases of sensing. So when we do that, you need a lot of data points related to that particular user. Suppose one person opt for a service where he wants to be his health monitored via node B itself. Okay. So now there is a lot of data points, and then we need a very beam-formed tracking of that user, right? So in that case, terahertz can come into play. Okay. Using terahertz, you can locate a user, track him properly, get the sensing information out of him, and then find how good he's doing. And then you can flag it what problem he's facing. So in these kind of situation, terahertz communication can be more handy and very, very useful. But so not directly, but indirectly, if I take it of the channel via the channel of sensing, it will be very, very, very useful in coming days. So we'll have to see how things unfold. We are still in study phase, but yeah, I'm very hopeful that things will have some good use cases in these regards.
Thank you very much, sir. Thank you very much. Now, can I move to, as a defense communication expert, I should ask to Dr. Jiten Prajapati. Sir has joined.
Yes, I'm here.
Yes, sir. What role should defense organizations play in accelerating terahertz innovation?
Okay, so I'll continue with the answer what Dr. S.S. Pandey was telling, that I mean, terahertz communication or terahertz system, when we talk about them, then we require a huge funding. Doesn't matter at what level you are working on, maybe system level, maybe one component level only. So you need funding. So as of now, funding is available, but those fundings are limited to premier institutes only. It is not open to all as of now. So if the funding is available for more institute, and then there is a collaboration between industry and academia, then it will be the advancement will be very fast in terahertz domain. Also, not just the funding, because when we see about the sources and the component of the terahertz system, then there is a challenge with the fabrication also. Sometimes we required specially made materials, sometimes we required very nano level fabrication. So those kind of facilities are not easily available. So if developing them for everyone is not possible, but at least whatever facilities we have, if it can be made available to everyone, all those who wants to do research in this particular area, then I mean it will be easy to work in this particular domain. So government can provide funding, as well as few centers where the fabrication can be done or the measurement can be done, then I mean it will be easy to work on these areas.
Okay. Okay. So expecting a one-line answer from you, that what will be the most transformative impact of terahertz communication on society by 2035?
So by 2035 you'll surely see that terahertz is in biomedical sector and in the industrial sector. So you'll be seeing that I mean they will be using it for their requirements. It will not be just application, means that they are just trying. They will be heavily dependent on these technologies. Also the communication, not the outdoor communication, the free space communication, but chip to chip level communication, indoor communication, terahertz surely will be there.
What impact in health sector will come?
Health sector means that, as in my talk I have already mentioned, that these frequencies, health sector, okay, so biomedical means that for imaging application and all those things, the biomedical related imaging application, sensing, I mean the most suitable word is sensing, that there you will be seeing that terahertz is there,
Okay.
and at very large scale.
Okay. 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 Thank you very much, sir. Any questions from audience, please? Any would like to answer? Ask? Yes. Any question from this one? No. Okay. Thank you, sir. Thank you.
Thank you.
So this is now for Professor Ekant Sharma, sir. Sir, how can academia contribute more effectively to national 6G missions?
Thank you, Dr. Chai, for this question. So, 6G missions, if you see, there are multiple ministries that are running 6G missions, right? Starting from DOB, which is the main institute which looks into communication side. But then not only DOB, Department of Telecom, there are multiple other departments also. For example, IT is there, CDOT is there, Center for Department of Telecommunications. So, and then CDOT, currently I'll be telling from my experience, recently has opened multiple Center of Excellence. Different institutes, like one of them is IT Roorkee, Gandhinagar, I think Kanpur, many other institutes. Why I'm naming them is, like, as a researcher, suppose, let's say, suppose I'm a researcher, I have no idea where to start. These venues are very good opportunity to understand what kind of 6G missions are running, what kind of problems they are floating. For example, CDOT always keep on floating some problems to the COEs, Center of Excellence. Like, for example, I'm giving an example of IT Roorkee Center of Excellence. It was just a few months back it was inaugurated, and a few months on we've got multiple problems of statements. And all the problem statements are very, very relevant. Like one of the problem statements that we got was for railway track monitoring. These are all part 260, like utilizing ISEC. And these are all part of government 6G missions, like how to utilize AI, how to utilize sensing, how to utilize RIS, how to utilize different aspects of 6G. but in a proper manner. It's not should not be only research like 99%, 99 out of 99.99% of the time we do research which is of no use. Literally speaking, I'm telling from here because it happens. We do some research or we just want to do some research, but if they're not at all implementable, then it just goes into somewhere, and even the guy who has written that papers, research paper is not ready. They're just doing for the sake of completing their requirement of their, I would say, promotion, right? PhD students are doing for getting degree, and suppose and all are doing for. So it's not connected to the output. But if we're, that's why I told at the starting, we're connected to the problems which our ministries are giving, like DOT is giving, or even like the MIT is giving, or for example, CDOT is giving, then as a researcher, we get an idea, no, this problem is important, relevant. Or for example, many companies are also there. Like I work with Samsung, Qualcomm is there, Nokia is there. They're also working on problems which are related to 6G. Not necessarily Indian 6G mission, but worldwide 6G mission. And they are trying to solve problems. So it's always good to frame problems which are relevant to the world or maybe India. Right? Otherwise, many times we just take some gimmicky problem which no one cares, and we also don't feel interesting. We are just going for the sake of getting some small benefit, like some promotion. The better would be that. And the best part is how to connect to them is connect with the ministries public. For example, nowadays multiple hackathons are happening, and UT and people are doing very nice. Like today only I got a call that okay, they're having a nice hackathon where industries are giving problems. When industries give problems, they are more relevant, and then anyone can pick that problem and solve it, and maybe get patent out of it, get research paper out of it, even get product out of it, which can be commercialized, open startup. So those problems can come directly from company that always help researcher, because our academia thinking is very different than company thinking, and when both together work, then that is the best part.
Thank you, sir. Yes. Any questions from audience? Any questions? Any queries? Anything?
Yeah, hello. Good evening, sir. And first of all, I would like to thank you for your excellent presentation. My question is, what funding opportunities are available for Terahertz research?
So funding, I would say, see, frankly speaking,
Am I
Terahertz.
audible, sir?
Yeah, you're audible. I would say Terahertz, if I would have said 3 or 4 years before, okay, it was at least in my field, everyone was talking about Terahertz. Right now, it has taken slightly backseat. Frankly, when I say backseat, because earlier it was thought that 6G will be about Terahertz is 6G. But right now, Terahertz and 6G are two different aspects. Terahertz, like in the previous talk also, I think I heard within that he was very right. That Terahertz will not be useful for outside communication, but inside. Now, limiting to that fact, why I'm connecting to that is because of that, the funding also, when it will come from ministries looking. So, for example, I'll tell you, I also got Terahertz project from DOT, Department of Education, I think 1 year before, and we wrote that project also 3 years before. But right now, getting projects on Terahertz, designing anything for Terahertz, and showing that this will be used for communication will require a good amount of conviction or motivation, and why communication in Terahertz is important, at least in cellular perspective, right? Like I was showing a testbed in the morning. When I was showing that, okay, that 170 gigahertz testbed, which I was showing, is not at all feasible for cellular communication. It may be feasible for very few distance, like meters of distance, not even meter also. Now, keeping that in mind, communication for communication research, if someone is doing, there are lots and lots of avenues, like DOT, like I said, CDOT is there, MIT is there, many other. But right now, this one new horizon has opened because of our government's effort. Many different European countries, which nobody knows. If you see that multiple European countries have opened their gate to write joint projects, like for example, Finland, Canada, Japan, UK, US, with every different, I would say, countries. You can write joint projects and all kind of topics are there, including terahertz, sub-terahertz, 6G, whatever you call it. So that is one nice opportunity that not many people are knowing. This is happening very, very recently. Like for example, there was one call for BRICS, from BRICS nations, that you have to have partners from any of the BRICS nations. It can be Brazil, it can be South Africa, it can be India, it can be China, it can be South Africa. So those companies. Many multiple research fellowship, research grants have opened, not only within India, outside India. I think within India, you guys all may be knowing about ANRF, with kids, ARP. Like this has been very much popularized. So within India, everyone knows what are the venues. Outside India, but not very many people know. And outside India, research grant maybe in school, like for example, they will not judge you based on whether you are coming from IIT or non-IIT. Outside India, it's mainly judged based on who are your collaborators. Like for example, India-Japan call is right now running, which is mobility program. You can submit a proposal by finding out some person from Japan who has interests similar to you, not completely overlapping, but slightly similar. You can write a project. There is one just 2 days back, someone told there's some call coming from Finland or Canada. So those kind of efforts also you can do. I'm not talking specific for terahertz only. Because all these things, they don't write specific topics. They just write life sciences. They write engineering science. They write general humanities. So then all these topics comes under that umbrella. In India, there's at least as far as I know, there's no specific call which says no, you have to do terahertz research, then only I'll give you money, otherwise I'll not. Most of the time it is communication specific, engineering field. So every, like for example, ARG when they give call, ECRG when they give a call, they give for engineering sciences. Engineering sciences, everything comes to. So it's better to look into India, within India also, and outside India. And right now, this is very, as far as I know, like last 3-4 years, the opportunities of getting funding has increased multifold when compared to it was earlier. I would say. Right now, if someone is genuine, someone is writing projects which are more relevant, not only theoretical perspective, they have some connection to like hardware. The chances of getting projects will be more when compared to when you have writing project proposal which are only on a theoretical perspective, not a hardware perspective. Chances like because everyone now we have understood like government has understood, everyone understood it's not only about your writing papers, it's more than that. At least something should be done. I would say that.
Okay, sir. Thank you very much. And thanks to ma'am also. Okay, ma'am. Thank you.
Thank you very much, sir. Now, with the panelists, after the discussing with all the panelists, as moderator, I should say that today's discussion has highlighted that terahertz communication is more than just the next frequency band. It's a cornerstone technology for the 6G era, enabling unprecedented connectivity, intelligent systems, and secure communication infrastructures. And as we discussed with you all, achieving this vision will require a strong collaboration among academia, industry, government, and defense organizations. Let's continue working together to transform research into real world impact and shape a connected, secure, and sustainable future. Over to you, Dr. Acha.
Thank you, ma'am. Thank you to all the distinguished panelists for an engaging and thought-provoking discussion. Now, as we approach the final technical session of today's summit, we are delighted to conclude our series of expert talks with an inspiring session on the convergence of artificial intelligence and next-generation wireless communication. So today, it is our privilege to welcome Dr. Sagar LNU, who is currently serving as a senior staff engineer and manager at Qualcomm. He is a member of 5G Access Stratum AS protocol team, where he contributes to the development and advancement of next generation wireless communication technologies. Dr. Sagar earned his Bachelor's of Technology in Electronics Engineering from IIT Dhanbad and his Master's of Technology in Communication and Signal Processing from IIT Madras. With nearly 18 years of rich industry experience, he has worked extensively on 3G, 4G LTE, and 5G NR technologies. Over the course of his distinguished career, he has held key engineering positions at Alcatel, Lucent, Intel, and Qualcomm, gaining deep expertise in wireless communication systems, protocol stack development, and cellular standards. He is also an innovator and researcher holding 5 patents in the areas of 4G and 5G technologies, which reflects his significant contribution to the field of modern telecommunication. Please join me in extending a warm welcome to Dr. Sagar LNU. We are honored to have him with us today and look forward to an insightful and enriching session. Over to you, sir.
Yeah, thank you, Dr. Jyoti and Dr. Chaya, ma'am, for the opportunity. So let me share my screen. Please let me know if it is visible or not.
Yes, visible, sir, visible.
Visible? Okay, sure. Thank you. So, hello everyone. As I think I have got introduced now, so I'll just quickly latch onto the topic which I have to be talking about. So the topic which I'm mainly focusing on is 6G, the next gen intelligent technology. So as we all know now, 6G is going to be intelligent technology considering all the AI game coming into the play. So I'll be focusing some of the aspects of it and we'll see how things move forward on it. So only 3 small topics, however, there are some couple of slides. So I'll be capturing the introduction and path ahead, and then how AI is helpful in that, and then some part of sensing, how AI and sensing are a game changer for 6G. So I'm just trying to adjust the sensing part also in this session to showcase how AI is actually helping, and along with the help of Terahertz. So to begin with, 6G is a successor, IMT 2030, and I think these two pictures has been shown already a couple of times. So I will not invest much time on it, but just to put the integrated, the ISAC, which is integrated sensing and communication, and AI are the key aspects of 6G. Totally new channels which has been defined in IMT 2030 and were nowhere present in the previous generation like IMT 2020. So 6G has similar goals: increase bandwidth, get low latency. But if you see these concepts like AI native air interface optimization, security, like Qualcomm, the quantum resistant security, which is something new, which is not there. I mean, I was also quite came to know about recently only. So these are some new topics like agentic AI, distributed intelligence and compute, sub-terahertz band and terahertz band, and immersive communication. So these are things which were like not present in 5G, and it's going to be core new items in the 6G. So that's why I just highlighted them. So with this, we will jump on to the main key topic which we have to target on. So AI native 6G with adaptive intelligence. So as we all know, right, AI is going to be one of the key feature of 6G. It's a totally new game changer for wireless industry, though AI has been present in some smaller formats across the different technology, because if you see in 5G also at UV level, we do some kind of learning and adapting. But as a broader level, if you go by 3GPP, this is the first time where we are actually focusing on 6G. So with adaptive intelligence, we expect that every device in the network is capable of doing AI on its own. So when I say, so that is the 6G goal, that every AI, every network element will be capable of running AI learning on its own based on either coordination or on our own. Anything, it's okay, but it will be AI capable if required, participate and contribute.
Excuse me, sir.
Yeah.
Your slide is not changing. Would you like
Oh,
to
sorry,
say
it's not
change it?
changing. Okay.
It is stick in first slide.
Okay, stuck. Okay, 1 second. Let me try once more. Give me a second. Let me reshare now. Let me share full screen. Maybe it's.
Yeah, now in next slide has come.
Next slides are coming. Okay, let me.
Yes.
Okay. I just changed. I'm just changing my slide. Just confirm it is showing or not. 1 second.
Okay.
I just changed. Can you see it's changing?
Yes. Now it's changing and it is visible.
Okay, sure. Thank you. Okay, so I hope we have not missed much things. So I'll just go to AI directly now.
Yes, yes.
So the expectation from 6G in terms of AI is that each device is capable of running AI on its own or in the coordination of network. So if you see the first example, like overlay AI ML, this was the case where there was no collaboration and device or network was running ML on its own. So for example, in our solution, also we have some AIs where we try to see that, okay, which cell to latch on, which beam to latch on, even without telling the network. So we try to optimize from our side also. So these kind of things are already present in 5G. But in 6G, if we go, the expectation is that every element can interact with each other in terms of AI, can do channel transfer. If there is a need, they can work in coordination hand to hand, and then they can transfer models or data as required, and then work as an AI entity. So the native AI ML is the goal in the 6G, where every device is capable of doing AI on its own. So this is the final goal from 6G perspective. We'll see what all use cases are there with the help of AI, which all use cases we are solving with the help of AI. So moving forward, as we know, right, the wireless has challenges as we can see here. Like the main challenges which we face is hard to model a problem. And as we know, with terahertz communication, it is going to be much more severe. And there comes the AI. AI is going to be a key player to handling the non-linear problems. So if there's a non-linear, when we say non-linear means the equation is like non-linear aspects and with multiple parameters associated with it. So AI is going to be expected to be, solving hard to model problems, computational infinitability of optimal solutions. So for example, if we have a network, okay, and we have like, right now we have 100 megahertz bandwidth. But going forward, if we go in the range of terahertz, the bandwidth can be in order of gigahertz. And in that case, you have to distribute your resources in such a way that it has to be optimal. Now that distribution is going to be very mathematical, computationally low heavy. And in that aspect, AI is going to be very helpful. So AI is going to be a very, a needed use case, needed tool, which is going to help 6G flourish, work faster and have better future. So we'll see how things unfold on these lines, but the expectation from AI is to help 6G become more, easily approachable, easily solvable. The complex problems should be easily solvable using AI. If you see another point which I have to highlight is 6G, using 6G. If I see even the current situation, we don't the changing of parameters doesn't happen very frequently. So if a parameter is changed from network side, we generally stick to it. But the expectation from adaptive intelligence is that based on the demand of the service, you change the parameters. So for example, if you see in this second picture, there is a training and AI ML. It will be pushing UE to change RRC, PDCP related parameters based on the demand of the needs. So suppose we have PDCP level, some timer is there to deliver the packet from lower layer to upper layer. Now, because of poor cell condition, there is a possibility that that parameter will not be optimal. So AI can help you in finding that what will be the optimal parameter to change so that the video play will be more smooth. So those kind of on-call, those kind of decision can be made much easier using AI because you'll have like multiple data across that region for multiple users. So using that information, your network can learn faster and implement faster. So that's what is the expectation from AI in 6G. And yeah, if any question, if there's no, we'll move forward. Okay, so moving to next slide. I hope slide is changing now. Can somebody
Yes,
confirm?
sir, slides are changing. Yes,
Perfect.
sir.
Okay. Okay. So if I go by explicitly by the 6G air interface use cases, I'm not going to core network. I'm not going to upper layer management. I'm just focusing from the lower layer perspective. So there are three main use cases which has been defined in 3GPP. I mean, there are some couple of more, but the mostly focused one are these. One is CSI feedback enhancement. So we have to find a way where AI can help us in giving the CSI feedback better. Second is beam management, as we all know, right? We were discussing millimeter wave, terahertz, will have multiple beams, too many beams, right, to handle on. Not only SSB beams, but then UV level beams, orientation level beams. So those kind of beam management is going to be, handling those using AI is going to be, expected to be easier. So that's why it's going to be playing a key role. And then third is positioning. So when we do positioning means, we will have positioning protocols where we can locate a UE using different TRPs. Right? So using different TRPs and then using AI on top of it, finding the accurate positions is one of the key aspects of the 6G air interface. So these are a couple of goals at the 5 layer to tackle on from 6G AI side. And I've taken one example in details in the coming slides, just to showcase how it is helpful. So moving forward. Okay, so this is one example, CSI feedback enhancement. So as we all know, like in 3GPP, network configures what all TRS channels you have to follow. And then UE has to measure the cell channel quality of that channels, and then feedback the channel quality indication, pre-coding metrics, and then rank indication, which will tell how many layers are there. And based on that, network will take a call, how many layers and all the RBs allocation and all the games. Now, if we take an example, like currently 3GPP supports type 1 CSF report and type 2 CSF report. So type 1 takes if I go by 100 for 100 megahertz bandwidth, the type 1 reports is of order of like some 10, like 20, 30 bits. If I go for type 2, it is in order of like 400 bits. So it is not very big number, but yeah, it's slightly bigger. But when we go for massive MIMO, multi-user MIMO scenario, right? The CQI or the PMI metrics which we are suggesting may not be optimal from network for network. So in that case, the discussion is there any way that we can report complete channel metrics, maybe in complete eigenvectors instead of H, we can report complete eigenmetrics. Even if this dimension is similar. So the discussion is ongoing that can we send the complete channel in some form to the network? But then the challenge is the payload will be very high. So I've just taken one sample configuration. If I have 8 antenna, very basic configuration, 8 antenna, 1 RX, 10 megahertz. Generally, we have 100 in 3GPP for TDD bands. And one bit, suppose one information needs 32-bit encode. We will need 3,19,488 bits to encode this much of a channel metrics, which is a huge number. Just imagine how much it will become if the TX becomes 64 or 128 or 64 or 256 for massive MIMO, and RX become 4, it is very very common norm in 3GPP, and bandwidth become 100 megahertz. So this number will become multifold. And since we have to keep reporting this metrics very frequently, like if you see in 3GPP, we report approx 20 millisecond, 40 millisecond periodicity, this data will be very huge to send it to the network. And that is a big challenge for 3GPP to tackle on. So here AI comes in the play. If you see, we have, I just took one picture from 3GPP only. So what we can 3GPP, one way it is being projected is auto encoder based CSI compression and feedback. So the goal is the data will be compressed using an encoder. So for example, you can use in encoder, you can use an AI network like CSI net, which will be working in CNN format only, like convolution and neural network. Using that approach, we will try to compress that bit. So for example, we'll take example like we calculated this number in the last bit. And we have seen that using some encoders, we can compress to only 384 bits. So these numbers can be compressed to this number, 384, with a compression ratio of 832. So instead of sending these bits, we have to send only 384 bits for network to decode it again. But yeah, with a caveat that your encoder and decoder should be properly in sync. There should not be the kind of training which encoder has will be decoder should have very similar training. And based on that, obviously he'll be able to decode the channel metrics out of these bits. And then, so now the problems will become a bit simpler for them. You have to send only small 3 to 4 bits, which is very small. We can keep sending it. It is very similar to type 2 CSI feedback. And that's where your channel performance will improve. So your AI will help you to compress the data in a smaller format so that you can keep sending it periodically without wasting the network resources. Okay, so if any questions we can take, I'll move forward. So Qualcomm, so in that aspect, Qualcomm did actually had a joint demo with Keysight, where we used this strategy to follow, and where we used very similar thing. It was 3.5 gigahertz channel, 100 megahertz bandwidth, TDLA channel kind of channel, as we all aware, like type delay line is A, and 8 ports varying rank and SNR. So what we did is we did same test case with release type 2 CSF feedback, and then we did with same test case with the AI based compression. And then it has been observed that for different SNR and rank, the gain was varying from 20 to 70%. So with the compression technique, the gain was in the range of 20 to 670% based on the SNR and rank. So this was one, what to say, this demo was presented in the Mobile World Congress also, where the Qualcomm showcased what is the gain which we can get with the AI in terms of channel state feedback improvement. Okay, so moving forward. Now coming to the, I think this is this question I have taken in the session also. So I was just trying to showcase how an AI and terahertz communication can help each other. So as I was answering at that time in my previous Q&A session, AI for terahertz, how AI can help terahertz. In a way, it can do channel modeling. Non-linear channel modeling can be easily handled by AI. Multiple beam management. As I was saying, like number of RBs will be very high, so resource allocation can also be taken by AI, signal processing and network optimization. So these I think we discussed. On the other hand, terahertz can also help AI. In what sense? Since you have very high data rate, right? So you can easily transfer the large language models from one entity to another entity. So suppose I have updated UE is running with some channel model, and for example, CSF compression only. One model is running at UE side, one model is running at network side, and I assume that both are in sync. But because of varying channel conditions, suppose it went out of sync, then terahertz communication can help in faster transmission of this AI models from UE to network or vice versa. Or it can send multiple training data faster using terahertz communication. So that way AI will be getting a help from terahertz communication. Similarly, massive bandwidth will help you in faster transmission, low latency, edge connectivity. So with using edge connectivity, your device can actually work as a network entity. So even it is not part of network entity, since the transmission between UE and network is so fast, you will not feel the lag, and you will feel that actually processing is happening on the UE itself, even if it is happening in the network side. High resolution impact. So using terahertz, you can get a high resolution data of a particular region or location, which can help AI to build, better efficiency and taking a better call that what should I do with suppose there's a blockage. Using better sensing, you can know there's a blockage, and AI will learn on top of it and then take a call that how it is going to help the user by moving the beam to different direction. So it's a symbiotic relationship. AI can help terahertz and so the vice versa. Okay, so I move forward. So now I'm touching the wireless sensing part, which is a very good use cases of AI and terahertz both. So I'll just cover basics of US sensing, and then we will quickly latch onto the benefits of using AI and terahertz there. So wireless sensing, as we all know, is a capability to detect, understand object motions and environmental condition using reflected radio signal. But there's a key difference compared to positioning. In positioning, we can only locate the position of those devices we have active network connection. So for example, mobile, or if your vehicle is connected to network via some SIM. In those devices only you can find the position. But it will not work for trees or for buildings. Those locations cannot be determined using the positioning. But for that, sensing is needed. Sensing can identify, okay, at this location building is there, at this location there's a big tree, something like that. Beside that, using sensing, you can define the characteristic of that object also. Is it a stationary object? Is it what kind of object it is? Is it human or building? What it is? So those kind of things can also be identified or known using wireless sensing. So if you see this picture, as I can see, I'm not sure I can show the laser here. No, I don't think it's possible. So I mean, as you can see in the image, like the blue lines are the transmitted line from node B, and the green lines are reflected from the objects. And using that, network can know which object. I mean, obviously there are multiple physical layer parameters like angle of arrival, radar cross section. Based on that, it will take a call that which object I am looking into it, and AI also, obviously. So this is what is the basics of wireless sensing, and we'll move forward on the 6G part now. So ISAC is actually it's a new term defined in the 6G, which is going to define sensing as a service. So till now, suppose you take the example of sensing by radar, right? Sensing by radar only says, okay, there's an object somewhere. There's a object approaching to this particular point or something like that. But with ISAC in 6G, it's going to be a service. By service, what I mean is, suppose I was, as I was giving example during Q&A session, if I need to monitor, suppose a person and his health, okay, an application can register to 6G services that, okay, you keep giving me the data of this user whenever I need from you. And based on that, so 6G can come in the play. It can do the sensing. It can get the sensing data for that user and it can keep giving to the application based on some charge. Obviously, it will not be free for him. So, and then based on that data, application can take a call that, shall I take any action or not? So it's a kind of service which is being offered via ISAC, which was not the case earlier. So this is why this is going to be a very key player in 6G. And there are multiple benefits of using ISAC, for example, deployment efficiency. So we are not putting any new hardware. The expectation is that whatever band we are getting as part of 6G, we have to use some resources of it for doing the sensing. Obviously, once you are not using any new hardware out of it, or you are not allocating a new bandwidth for it or band for it, the spectrum efficiency will be there. Energy efficiency will also be there as there's no new hardware transmitting. And scalability and flexibility is easy because 6G we can scale at any level whenever we want and at whatever location we want. So that's why ISAC is going to be a very key player in 6G. It's going to be one very new horizon, not from the user perspective, but from the network perspective also, because it will be a new revenue resource for them. It can respond new services. Based on that, it can generate a new revenue using ISAC. So we'll move forward again. As we can see, there's ISAC unlock new opportunities as I was talking about earlier. So the few is like drone detection, automotive maneuvering, crowd management, digital twins. You can, I mean, by digital twins, you can find a replica of an environment. Where is what? So for example, in the location, there are like couple of buildings and then there's a park and those things. So you can create a digital twin of that for better sensing and identifying the location. Then obstacle management. So you can identify if there's a obstacle in, so for example, the railway track obstacle. You can easily find, okay, using sensing, we can find there's obstacle ahead. Weather and flood monitoring, which is a very big use cases for and very applicable in current scenario. So you can identify if there's a particular location has more water log, it's kind of flood kind of situation. You can know upfront, you can find using 6G sensing and then act on it. Okay, maybe you can release a stress signal or emergency signal that, okay, avoid this route, something like that. Health monitoring, as I think we just give some couple of example on that. So health monitoring is also one key aspect where we'll be monitoring, we can monitor a user and his health based on the need, based on his subscription. You can use this service to identify if there's any external or internal intruder or not. So it's a very good use case where using 6G sensing, you can find if there's somebody outside which is not supposed to be there. Suppose you are living in some remote location and then there are some animal which can be coming across around your house. There's a possibility that. So using that sensing, you can find there's some problem there and you can act on it. Network efficiency and performance, I think we had a long discussion on that. So ISAC can help because it will help you easily locating where is what. So suppose you know that at some particular location there is a building and because of that the signal is getting blocked, or suppose there's some location there's a tree, because of that the signal is getting blocked. So network can take a call, okay, shall I move this call from this TRP to some other TRP, and that way your network efficiency will improve. So this way ISAC unlocks some new opportunities and use cases in 6G. These are properly defined in 3GPP and very much applicable, especially in India context. If you see the crowd management, pedestrians obstacle on railways, water and flood monitoring, health monitoring. I mean, there's quite good use cases which are very common in India, and I'm sure that this will be a new role. This will play a new key role in improvement of the network performance. So we move forward. So ISAC has like some three types of modes. One is monostatic. Monostatic means there will be only one transmitter and that only will act as a receiver. So for example, if you take the first picture, the network is transmitting to UE and his network itself is monitoring the reflections coming from the UE or scattering coming from the UE. Similarly, other way, mobile is transmitting to a user, and then it's monitoring the reception, the scattering from that, the receiving from that user. Another is bistatic. So it means there can be more than one entity in place. So for example, first, if you see this example, there are two TRPs. So one is transmitting and other is listening. So that way, so the one which is transmitting is not the receiving entity, but the other entity is the other TRP is the receiving entity. So this is bistatic. And then comes the multistatic, which is going to be more useful case, and 3GPP is mainly focused on multistatic use case scenario in 6G. So in multistatic, there can be more than one transmitter and more than one receptor, but there will be sync via some means, via core network, via sensing function. So via that, they'll be coordinated across them, and then you can get a better feedback on the user. So suppose there's one UE user moving somewhere, and then you monitor it via multiple TRPs and multiple mobiles even. You can locate him in much better way than the previous use cases. So 6G targets on multistatics, so that the performance can be better when it's seen using sensing. So we'll skip to move to the next slide. As I was saying, terahertz millimeter wave bands are going to be a key player here, though mid bands will also be helpful. But why I'm focusing on these two bands is because, as we all know, right, the resolution of a location measurement is inversely proportional to bandwidth. Now, if as we all know, right, in NR-TD bands, we can have 100 megahertz. If we go to FR3 bands, which are like upcoming bands in the 6G, it's in the range of 400 megahertz or 500 megahertz approx. So the bandwidth is like, it has increased 4 to 5 times. So we expect the resolution of mapping will also increase by 4 to 5 times. So this is what expectation is for mid bands. But when we move to millimeter wave or sub gigahertz or terahertz band, the expectation is that your bandwidth will be in the range of few gigahertz. So I'm not in Qualcomm only we did some we had some test where we had bandwidth in the range of more than 1 gigahertz. So if you just compare with the mid bands, it will be like 3 gigahertz, almost 6 times of the bandwidth supported there. And if you compare with the current NR, it's like 30 times more. So the expectation is that your resolution, which you're going to get as part of terahertz or sub terahertz, will be multifold, like in the range of like 20 or 30 times compared to current one what we have. So that's where terahertz communication millimeter wave will be a key game changer, because they'll be helping 6G ISEC to have a very fine granularity level identification of objects, and then sensing function can do the modeling of them, and then it can take a better call what to do with the network resources, how to make sure that there is no call drops or data fluctuation, those kind of things. So we'll move forward on this now. Yeah, so just a couple of slides on how 3GPP
Any questions, please write in the chat box. Any curious? Participants, please write in the chat box. We'll ask you. Okay, sir, you continue, please.
Okay, sure. So ISAC was mainly first studied in 3GPP release 19 as part of 22.837, where they defined multiple use cases for what kind of scenarios we are trying to cover. So as we saw in the previous slide, if it is a flood case or automotive device car management, or objection, if there's a pedestrian or something, object detection, those kind of things are there. So those kind of use cases 3GPP had defined here in release 19. They defined what will be the success rate for them for the detection. All kind of key KPIs for the detection of that particular object was defined there in release 19. But it was early stage, mainly, and there in 5G was also discussed as part of ISAC. But then there was quite limitation when it comes to the 5G advanced and 6G ISAC. So as we can see, right, the sensing mode, if you see the sensing mode, it was only primarily monostatic. So only network can transmit and receive. But as I was showing in the earlier previous slides, 6Gs can have monostatic, bistatic, multistatics, where anybody can be transmitter and the receptor. So obviously we'll have better better granularity or better resolution to detect the things. Reference signal, 5G uses a previous obviously existing channel. So Qualcomm had a drone based Qualcomm did had some tests, and it showcased that ISAC is definitely possible, but using 5G channels. So it has shown using 5G, but the expectation from 6G is that you can use dedicated sensing reference signal, which is explicitly defined for sensing part. So for example, if you see this chirp signals, right, which is used in radar. So those kind of signals are also being studied in 6G, though not materialized yet. But all the radar signals are also radar channels are also being in discussion for taking a call that what will be the final outcome. It is still yet to be concluded, but they are also being discussed. The third point is higher bandwidth. Obviously, as we discussed, NR has like 100 megahertz. 6G is supposed to be have 400 megahertz plus. Multi-level participation. So we have just discussed this. And then the one more important aspect is intelligent data processing and architectural exposure. So in 6G, it is expected there's a new entity like sensing function. If you see the bottommost row of the photo, there's a sensing function, SNF. So it is a new entity got introduced for 6G, where it will take care of all the application requests and to use sensing as a service. So as we discussed in the previous slides, we're saying like sensing in ISAC is going to be a service where any application can register for it and ask for a sensing data to take a call what to do with a particular user, right, charged user. So this will be totally new in 6G, and that's how like 5G ISAC is just a basic stepping stone. But we expect that 6G is going to be the actual use case where the ISAC will be implemented. Okay, so we'll move forward on this. Yeah, so as I was saying that sensing is a service, going to be a service in this 6G. So as it is going to be service in 3GPP, now we are going to have security also being provided. So whatever app request for it has to be properly encrypted. There should be a proper spec defined for it. And sensing results, both 3GPP, non-3GPP data also has to be passed to them. Operational challenge has to be taken care in that, and then configuration and authorization. So only the people who needs it should be given it. I mean, whoever is authorized to use should be given the sensing data. So I mean, what indirectly what this slide wants to say is that ISAC is going to be a service which anybody can register for if needed, pay for it, and you will get a secure data. Nobody can latch on it. It will be a secure data authenticated to you, and whoever is the privy of it, only that is going to be the recipient on and then act upon it. So these are like couple of requirements which 3GPP is going to solve, so that ISAC will be the full-fledged work as a service provider to application and a revenue generator for node B and user maybe. We'll have to see. Okay, so we move forward. So release 19 study was mainly focused, as we were saying, right? It's saying we have 32 use cases defined in this spec. And then there was some channel modeling also had happened in that spec. So in 38.901, it has given a detail that how you can define an object, what is the radar cross section. So radar, just to give a small overview, radar cross section means it tells you how much of the signal has got reflected or scattered from a object and reached to the network. So based on that RCS, you can define what is this object. So based on the radar technology in past only, for each frequency, for each user. So for example, for humans, it can be in the range of 0.1 meter square to 1 meter square. So it's your RCS can be in that range. So if the network receive in that range, it can think that this can be a user, a human. And then mobility, clutter scattering, all those details for an object is given in 38.901. So these are a couple of parameters which they have given: sensing targets of position, dynamic blockage, multipath, clutter, background scatter, target orientation, radar cross section, target mobility. So these all parameters, in what range it has to be, with what object it can be, has been given in 38.901. So 3GPP release 19 gives a very standard a guideline that how and what will be the criteria for an object to be detected in out of available in the environment. So for example, is it object is a human, drone, buildings? For all these, what will be the criteria to define them? What will be the how to identify them? Those all modeling is part of 38.901. Move forward. Then we release 20 came, and release 20, there's a new spec came 38.765. It gave the performance metrics that what will be the performance when we are trying to identify objects. So it gives for each object, for example, UAVs or human, it gives you what will be the past performance metrics. So for example, if you see this table, it has given a scenario. So what is the scenario? It's just a number, you can ignore that. Number of TRPs of which target is model. So this is a aerial vehicle model. So you're going to identify a aerial vehicle, means drone, using multiple TRPs. Frequencies can be anyone. So and then so example, and the TX power is 52 dBm. Sensing resource ratio is less than 10%, means out of available bandwidth, for you are using less than 10% for sensing. And then number of horizontal and vertical TX beam is 1. So only one antenna beam is being used across the TRPs. And so it has been observed by 3GPP that if I use multiple TRPs, in this case, we can easily detect your misdetection probability can go less than 0.89%. It means by misdetection, I think by the name itself suggests the object is there, but we cannot detect it. That is your misdetection. So your misdetection probability should be 0.89, means out of 100 detections, you should be not able to detect only 0.9, right? So these were the performance metrics has been given in the 3GPP release 20, that so that your performance metrics can be defined, and if it is falling in that range, you can say that you are satisfying the 3GPP criteria to identify or locate a object. Okay, so these are the progress which has happened in 3GPP till now in terms of ISAC. And this is one new function, that's sensing function, which I was talking about earlier, has got introduced in this release 20. Though not much details are available, but the expectation of sensing is the sensing function is to do all the AI related stuff and then actually identify the object that which category it falls in. So if you see the top blue line, that there are some sensing reports, measurements, level B, C, D. Just to give you some small details on that. So whenever there's an application, if I go to the right most of the picture, application, the orange color one, right? There's automotive, UAV, smart city, and all those things. Right? So they need, suppose they need some sensing information. They will put a request to the core network, and core network will pass it to the sensing function. Now sensing function, based on the requirement, suppose somebody needs to locate a example, UAV we just discussed, right, in the previous slide. So for example, in UAV detection, maybe we need multiple TRP. So sensing function will take a call, which all TRPs shall I select for detecting that UAV. So based on the past data, past location where it is latched to, it will find nearby TRPs and it will take a call that, okay, which all TRPs should I ask them to do the sensing for that particular use, for that particular aerial vehicle. So it will send a control information for control configuration, and the expectation from G node B and the respective TRP is to send some measurement data. Now, as you see, there are level B, C, D. Level B, C, D says that what level we are in, which stage we are in. Has we detected already the object or not? Has we already zeroed down on the object or not? So suppose we have already zeroed down the object, you are just tracking it, that where it is moving to, then level D is good enough. It's the smallest information. But when you are in very initial stage, you have not located the user completely, then you need level B. Actually, there is a level A defined, but level A is not supported right now. So we are, suppose the lower we go, suppose B, C, D. So the lower number, suppose B will have bigger data, D will have smaller data, which makes sense, right? But as you are already zeroed down, you will need lower data, lower information to track it. But once you are not located it, you are still in detection phase, you will need more information about it. So sensing function will ask GNodeB to do a periodic measurement and keep giving the data, and it will keep sending the measurement report via GNodeB. And then sensing function will have all the data, AI processing, location handling. You can see that like very detailed entity it has been. It has all the use cases related to serving sensing, policy and authorization, sensing request, session manager, policy authorization, GNodeB TRP selection, and time synchronization. So it does all the key part related to sensing, and then it will process also. So it will, after receiving all the data from GNodeB, it will do the post processing, take help of AI also, and then take a call okay, is it an object or not? What is the location of it? How fast it is moving? How is the angle of arrival and other aspects? So all the key aspects related to that object will be decided by sensing function, and then it will pass it to the application as required. So this is a very key module which is coming up on sensing as part of ISAC. Okay, so we move forward. Now, how the terahertz bands is going to be used in 6G for ISAC. So as we had discussed in past also, like obviously terahertz enables simultaneous ultra high speed communication with high resolution, but challenge is propagation and blockage, and hardware must be addressed for 6G deployment. So as we know, right, 6G we can have like higher bandwidth. We can have bandwidth in the range of like few gigahertz, 3 gigahertz, 5 gigahertz in those range. So in that regard, in those range, your throughput might not get much impacted, even if I put some resources for sensing. So that will have a benefit for sensing use when we use terahertz bands. Another point is, as we know, right, since we have bandwidth in the range of 3 gigahertz and more, your resolution will be much better in you detect an object. Multipath, since we have like very tight, very thin beam we can achieve using millimeter in terahertz, you can precisely locate the user using multipath. And yeah, high bandwidth for resolution sensing, and yeah, low probability for interception. Since your bandwidth is in a range of like gigahertz, the interception is not going to be very easy for them. But then challenges are also there, as we also know. Terahertz communication is very much impacted by path loss and environmental condition. It has LOS line of sight dependency. Components costs are also higher. Hardware impairments are also there. And then beam management is also challenging for terahertz, as we discussed AI there. So yeah, these are the challenges associated. But then with terahertz higher bandwidth, it is expected that it will help ISAC, which is a very key pillar of 6G in coming times. So with this, yeah, this is what I have from my side. If there's any question, I can take.
Any question from audience? Over to Dr. Ajay.
Any questions, anyone?
Okay, so I think we can stop here then. Thank you.
Thank you very much, Mr. Sagar LNU, for your enlightening and thought-provoking presentation. Your insights into the transformative role of AI in shaping the future of 6G wireless networks have been truly inspiring. We sincerely appreciate your valuable time and knowledge you have shared with all of us today. So, as a token of our heartfelt appreciation and gratitude, please accept the certificate of appreciation and momentum. Thank you, sir.
Thank you.
Thank you very much.
Thank you.
As we come to the close of today's summit, I invite Dr. Chaya Dalela to summarize the summit. Over to you, ma'am.
Yeah. Thank you, Dr. Achal. Namaskar and good evening to all. With the divine blessings of His Holiness, Sri Jagadguru, Sri Shivratri Deskandra Swamiji, Honorable Vice Chancellor Sir, JSS University Noida, the Department of Electronics and Communication Engineering organized one-day online summit on JSS Terahertz Horizons 2026, exploring the next frontier of ultra-fast communication. The summit witnessed an overwhelming responses with the terms of registrations, bringing together academicians, policymakers, industry experts, researchers, professionals, and students from across the country and abroad. Through insightful expert talk and engaging panel discussion, the event served as an excellent platform for exchanging ideas on current trends and future vision of 5G and 6G technologies, 6G and terahertz commercialization pathways, cutting-edge research in RF, terahertz communications. The deliberations throughout the day, definitely I can say, reinforced India's commitment towards 6G technologies, the development of AI-driven wireless networks, IoT, and next-generation communication system with the India 6G vision for a sustainable future. As we conclude today's summit, let's reflect on some of the key insights that emerged from the expert sessions, panel discussions, and the discussions with the audiences. Number one, that I can see that 6G is the envisioned as an intelligent AI native network that will integrate terrestrial, aerial, satellite, and underwater communications, providing seamless global connectivity. With the other side, terahertz communication is expected to play a vital role in achieving ultra-high data rates, although challenges such as propagation losses, hardware development, and efficient antenna design remain active research areas. Also, artificial intelligence and machine learning will be integral to future wireless network, enabling intelligent resource allocation, self-optimizing networks, predictive maintenance, and enhanced security. Very importantly, in my perspective, industrial academia collaboration plays very important role, and it is essential to bridge the gap between research and practical implementation through online projects, internships, innovation hubs, and technology transfer. Lastly, cybersecurity, sustainability, and energy efficient network design will be key priorities in the development and deployment of future communication systems. As our experts shared, that interdisciplinary research combining communication engineering, AI, electronics, material science, and computer science will drive innovation in 6G and beyond. Now, as summit closing remarks, I would say that today's summit has provided a valuable platform for exchanging ideas, sharing cutting edge research, and strengthening collaborations among academia, industry, and research organizations. The discussions have reinforced that the journey from say 5G to 6G is not merely an evolution of wireless technology, but a transformation towards an intelligent, connected, and sustainable digital future. Let's carry forward the knowledge gained today into our teaching, research, innovation, and collaborative efforts. Together, we all together can contribute meaningfully to shaping the next generation of communication technologies. Thank you all for your active participation, and we look forward to you all to meeting you again in future academic and research initiatives. Thank you. Over to Dr. Acha.
Thank you, ma'am. I now request Dr. Jyoti to deliver the vote of thanks. Over to you, ma'am.
Respected dignitaries, HODs, faculty members, and dear participants, a very good evening to all of you. As we come to the conclusion of the one-day summit, JSS Terahertz Horizon 2026, it is my privilege to propose a vote of thanks. Today has been an inspiring journey through the exciting world of terahertz communication, 6G technologies, and future wireless networks. The insightful technical sessions and engaging panel discussion has enriched all of us with new knowledge and perspectives. I sincerely would like to thank the Vice Chancellor, Dr. H.R. Mahadevaswamy, for carefully curating this summit, and to our acting Vice Chancellor, Dr. Manoj V, and the summit chair, Dr. Jagdish RS, for their unwavering support. And I would also like to extend our gratitude to HOD ECE for guidance. And our sincere and deepest appreciation goes to all our distinguished speakers, Mr. Shashi Shekhar Pandey, Mr. Lakshmaya P, Professor Ekant Sharma, Dr. Jitendra Prajapati, and Mr. Sagar Elinu for sharing their expertise, valuable experience, and insights that truly broadened our understanding on terahertz. I would also like to extend my sincere thanks to all the dignitaries, faculty members, researchers, industry experts, and participants who joined us today. A special word of appreciation also goes to our organizing committee for their teamwork and behind the scene efforts. And lastly, I would also like to acknowledge everyone who managed the online streaming and technical support. Thank you for your thank you to all the participants for your presence and support. Jai Hind. Thank you.
Thank you, ma'am. Finally, I request everyone to kindly rise for national anthem.
विधाता पंजाब जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you so much.
Have a wonderful day. Thank you.